Welcome to the course Magnetics for Power Electronics Converters. Magnetics are a very important part of any switching converter, and we need to understand how to model the magnetics, how to understand what's going on inside of them, especially to understand their loss mechanisms, and sometimes we need to design magnetics. So in this course we're going to talk about those things. The course has 4 modules, and the credit version also has a final exam. The first module on basic magnetics is about modeling the magnetic devices of a switching converter. I expect that you've taken courses in the past about magnetics, at least in a physics, electricity, and magnetism course, and maybe in an undergraduate course in electrical engineering. We're going to start at the beginning with basic magnetics, talking about the basic laws such as Faraday's law and Ampere's law. Then we'll use those to develop equivalent circuit models, we call magnetic circuits, for the magnetic devices. We'll talk about inductors with air gaps and about transformers, and we'll talk about the basic loss mechanisms of core loss and copper loss. The second module is on AC losses in magnetics windings. This is the skin effect and the proximity effect. In many switching converters, the proximity effect is one of the largest loss mechanisms in the converter, if not the largest. In fact, often the 2 largest losses in a converter are the switching losses of the semiconductor devices and the proximity losses of the magnetics windings. So it's important to understand how these losses work. I'm going to derive some of the basic equations that you can use with a simple calculator or pencil and paper to work out the proximity losses and skin effect losses in most cases. Module 3 is about inductor design. We'll ask the simple question of how to design an inductor for your switching converter. So we need to choose a core size, we need to give it an air gap perhaps, we need to choose wire, decide on the number of turns, and so on. So we'll talk about the issues of how to design inductors in this third module. The final module is about transformer design. The design processes are a little bit different than in filter inductors, and in a transformer we generally need to choose the flux density to minimize the total core loss plus copper loss. So we'll talk about how to do that, and we'll do some examples both of filter inductors and transformer designs. In this brief lecture, I'm going to review the basic magnetic relationships. While I'm going to assume that you've seen this before, perhaps in a sophomore physics class, I'm not going to assume you remember it, and we're going to just quickly go through what all the basic quantities are and the basic relationships. So we will take this from the viewpoint of considering that we have, say, an inductor or some other magnetic device that has a winding, one or more windings, and the object is to find the electrical relationship between the voltage and the current of the winding. To do this, we're going to have to relate the voltage and current to the magnetic fields inside the inductor, so that we will relate voltage to flux and current to magnetic field H. So this is a summary of the basic quantities. The voltage on a winding is related through Faraday's law to the magnetic flux through that winding. The current through the winding is related through Ampere's law to the magnetic field H in the core. And then the relationship between the flux and the magnetic field in the core is given by the core characteristics, or its BH loop. To get a physical feeling for what the magnetic field H and the flux density B are, I think it's useful to relate these to electric quantities. So we're used to talking about voltages in electrical circuits. The voltages are related by the electric field, so that if we have, say, some uniform electric field between 2 points, say there's a point x1 right here and another point x2 somewhere else in space, and if we have an electric field between them, E, that is uniform, then we can find the voltage or electromotive force between these points by integrating the electric field. In a simple example, suppose the points are 1 centimeter apart and we have an electric field between them of 10 volts per centimeter. Then we would measure 10 volts of voltage difference between the points. We can think of magnetic fields in a similar way. If we have 2 points in space, again x1 and x2, and we have some magnetic field H between them, then we can find the magnetomotive force, which is the magnetic analog of electromotive force or voltage. And we can find that magnetomotive force by integrating the magnetic field between the points. So if we have a uniform magnetic field, say in MKS units of 10 amps per meter, and the points are 1 meter apart, then we would have a magnetomotive force between those points of 10 times the 1 meter, or 10, in this case amps are the units of magnetomotive force. The magnetic analog of current is flux. So we're used to thinking about, say, some magnetic conductor, say a wire or some electrical component that has a current flowing through it. And we can talk about the current I that flows through the component. We also might talk about the current density at some point in the wire. And to find the total current, we integrate the current density over the cross-sectional area of the wire. For a uniform current density, the total current is the current density times the area of the wire. We can do the same thing with magnetic elements, and so we think about magnetic cores where flux flows down the core. And so the flux is the analog of the electrical current. And we can talk about flux density B. The total flux is the flux density integrated over the cross-sectional area of the core. With a uniform flux density, we can say that the total flux is the flux density multiplied by the area. So we have the analog of voltage, which is magnetomotive force. We have the analog of current, which is flux. So here is the formal equation that relates magnetomotive force to the magnetic field H. Basically, this is the integral of H dot dl, where dl is a length element on the path between points x1 and x2. If you integrate H along that path, you get the total magnetomotive force between the points x1 and x2. So again, this is similar to integrating electric field between 2 points. Here we can integrate the magnetic field between the 2 points to get the total magnetomotive force. In this class, we're not going to have to really integrate. We're going to have uniform fields, and so the magnetomotive force is the uniform field multiplied by the distance between the points, and we will commonly write the equation like this. And then here's the formal equation for flux density and flux. The total flux is the integral of the flux density over the cross-sectional area of the core material. If we have uniform flux density, then this integral reduces simply to the total flux is the flux density times the area. So we have some cross-sectional area, AC, multiply flux density B times AC, and we get the total flux. Okay, now let's talk about the basic equations. These are really Maxwell's equations. Faraday's law is the first one. Faraday's law says that if we have a loop of wire, here I've drawn a square loop, and it has, say, some terminals here at the end of this loop. If there's a total flux phi passing through the interior of the loop, that flux can induce a voltage in the loop. And so we'll measure a voltage V here at the terminals that is given by the derivative of the flux. Okay, so V is d phi dt for a single turn of wire or a single loop. If we have a uniform flux density, then we can, again, as on the previous slide, relate the total flux to the flux density. So the flux density times the area, this area of the loop, is equal to the total flux. And so we can write that the voltage in the winding is the cross-sectional area of the loop times dB dt, the derivative of the flux density. So Faraday's law relates B to voltage. We're going to be talking in upcoming weeks about Lenz's law. Lenz's law we could think of perhaps as a corollary of Maxwell's equations and in particular of Faraday's law, but it has a very important physical interpretation. What Lenz's law says is if we take our loop of wire and we short it out, so say we short it right here, then this flux will induce a current that flows around the loop, and that current will induce a flux of its own that tries to oppose changes in the original flux. Okay, let me explain that a little. Instead of shorting, let's just suppose this is a real wire that has some resistance, and I'm going to just model that resistance with a resistor here. Okay, and so when we have dphi dt, some flux changing through the loop, it'll induce voltage across this resistor, and that voltage will cause current to flow. Here, the way I've drawn this, we have to use the right-hand rule. The flux is passing from left to right through this loop. It induces voltage that causes current to flow in the counterclockwise direction around the loop. Okay, if you use the right-hand rule to see what flux this current induces, it will induce flux in the opposite direction. And Faraday's law will give us the voltage, divide by the resistance to get the current, and that then determines the flux that actually opposes the original flux. Because Faraday's law has a derivative, what this current actually does is it opposes changes in the original flux. So if we have an original flux phi of t that has a derivative, it will, by Faraday's law, induce a current that flows around the loop that makes its own flux that goes in the opposite direction and opposes the original change of flux. Okay, in fact, if you have a superconductor with zero resistance, it turns out that the induced current allows no change in the flux. With practical conductors that don't have zero resistance, perhaps there's a little less induced flux and there is some change allowed. The lower the resistance, the less change in net flux will appear. Lenz's law is in fact the mechanism, we can think of it as the physical mechanism that induces eddy currents. Lenz's law explains why eddy currents are induced in magnetic cores, and it also explains eddy currents in conductors, which we will see explains the skin effect and the proximity effect. The next important law that we will use is Ampere's law. Ampere's law says that the net magnetomotive force around a closed path is equal to the total current that passes through the interior of that path. And in integral form, we can write that the integral around a closed path of the magnetic field H dot dl, where dl is a unit length around the path, that this is equal to the total current that passes through the interior of the path. We aren't going to evaluate integrals that are any more complex than ones that have constant h. And so what we do is we choose a closed path that is the path that the magnetic field actually takes. So let's say we have a magnetic core with some turned wire on it, and we will have magnetic field that goes around what we call the magnetic path, which is the path around the inside of the core. So if you integrate h dot dl around this path, what you get is, for constant h, is h times the distance around the core that the flux takes going around the core, which we call the magnetic path length. Okay, so H, this constant H times the magnetic path length, is equal to the total current that passes through the interior of this path. In other words, it's the total current that goes through this window or hole in the middle of the core. So let's suppose there's a wire, one turn of wire that has a current I flowing through this. So we'll have current I going down into the page, going through the interior of this path, and Ampere's law tells us that H times Lm is equal to that current I. Okay, so Ampere's law then relates the magnetomotive force, or the H field, to the winding current. And in fact, the integral of H dot dl is magnetomotive force. That was from an earlier slide. This is the integral of H dot dl around the entire path. And so the magnetomotive force, H dot dl around the whole path, is equal to the current, and the currents in windings are sources of magnetomotive force. One further implication of this is that the total MMF around a closed loop is zero, as long as you account for winding current. So what we just said here, Ampere's law, is that this is the total MMF around the path, and this is the total current passing through the path. So we can say that if we have a closed loop and we account for the sources of MMF from the winding currents, they're equal to the integral of H dot dl around the path, and they all add up to zero. Okay, so we've related winding voltage through Faraday's law to B, or flux. We've related winding current through Ampere's law to H, or magnetic field. Finally, we need to relate B and H, and the relationship between B and H is determined by the core material, or the material properties. So if we have free space, or air, say, or a non-magnetic material, we can write B is equal to mu naught times H. This turns out to be a basic property of free space. Flux density is equal to a constant, which mu naught, which in MKS units is 4 pi times 10 to the minus 7th henries per meter. And so H and B are linearly related like this. In a magnetic core material, such as an iron core or ferrite core, there is a highly nonlinear relationship between B and H, which has both hysteresis and saturation. So it's a pretty strange and complicated relationship. With positive H, you increase B and you go up the right-hand side of this hysteresis loop. When we turn around and have reducing H and B, we'll go across the loop and go down the other side. So there is hysteresis. There's also saturation, where there's a maximum B beyond which the core saturates. So it's common in the magnetics business to use piecewise linear models of this, and the simplest one is to ignore both hysteresis and saturation and simply write that B is mu H, where mu is the slope of this curve, which might be the slope of the BH loop for, say, increasing B over small values. So we can linearize. In magnetic core materials, typically mu is much greater than mu naught. And so then we can define a relative permeability, mu sub r, where this mu is equal to mu naught times some multiplying factor mu sub r. And in iron and ferrite materials, mu sub r might be 1,000 or 10,000 or some similar number. We might also model saturation, and in that case we say that at some value of B that we call the saturation flux density, B sat, the core saturates, and in that case B becomes constant for larger values of H. Actually, it turns into something approximating an air core device, where this curve has a slope of mu naught at large values of B. Typical values of B sat are 0.3 to 0.5 teslas for ferrite, a half to 1 Tesla for some powdered iron core materials. For iron laminations and met glass and other materials, B sat might be 1 to 2 teslas. Okay, we have to talk about units. In the magnetics business, units have been historically pretty complicated. Today, the IEEE tells us to use MKS units, and that's what we'll use here in this course. The MKS unit for B, or flux density, is the Tesla. The MKS unit for H field, or magnetic field, is the ampere per meter. And the MKS unit for Weber, or for flux, is Weber. And in MKS units, we have B as mu naught times the relative mu times H. In older books and in some American manufacturers' core material data sheets, they use the older unrationalized CGS units. And in CGS, mu naught is defined as 1. So B is the relative mu times H. In CGS, the unit of B is the Gauss, and a Gauss turns out to be 1/10,000th of a Tesla. The unit for H is the Oersted, and here's the conversion factor for that. And the MKS unit for flux is the Maxwell, which is related to the Weber with 10 to the 8th, a factor of 10 to the 8th. The problem with CGS units, and why we don't like to use them nowadays, is that the common electrical quantities, such as the volt and ampere and ohm, are MKS and not CGS. And so there are conversion factors between the electrical quantities, and so you have to be careful in using these. And what I would suggest in this class is that if you encounter things like Gauss on data sheets, that you simply use these conversions and convert them into MKS, and then all of your quantities will come out in nice volts and amps and the usual electrical units. Okay, so let's do a simple example. Let's solve an inductor. So let's say we have some magnetic core here that has a core material with some permeability mu, and we put N turns of wire on this core, and the object is to write the equations and ultimately to find the relationship between the terminal voltage and the terminal current. So the way we proceed is to use the equations we just talked about. Faraday's law says that the voltage induced in one turn of wire is d phi dt, where phi is the flux passing through the interior of that turn. So here we have, say, one turn of wire that goes around the core and it comes back right to here. And I've defined some flux phi that is flowing around the inside of the core, and that flux passes through the interior of the turn, so it induces this voltage d phi dt in that turn. Now our total winding has N turns, and each turn has the same flux phi passing through the interior, so the total terminal voltage is N times this d phi dt, like this. And finally, phi is related to flux, where phi is B times the cross-sectional area, where here we're defining the core has a uniform cross-sectional area A sub C. So if you plug that into here, we can replace phi with BAC, and so the voltage is N times AC times dB dt. So this is our first equation that relates B in the core to the voltage on the winding. Next, let's use Ampere's law to relate the winding current to the H field, or magnetic field, in the core. So for Ampere's law, we follow the path that the magnetic field takes going around the core. So, and we'll assume here that the core is uniform, so by symmetry we'll have a uniform magnetic field H. And Ampere's law says the integral of H dot dl around this closed path, which is simply the H magnitude times the path length Lm of the core. So Lm is the distance, say, from here going around the inside of the core once and getting back to there. That H times Lm is equal to the current passing through the interior of the path. So the current passing through the interior of this path is the net current through the window or the hole in the middle of the core. Each turn carries current I, so this first turn has current I, second turn has another I, and so on. So within turns, the total current will be N times I. Okay? So I is related to H through Ampere's law. Okay, finally we have the BH characteristic of the core material. Here's our piecewise linear model, which we'll use. So as long as the core doesn't saturate, so when B has magnitude less than the saturation flux density of the material, then we can say that B is mu times H, where mu is the permeability of the core in MKS units. Okay, when we have values of H larger than this, then we saturate. So what value of H does it take to saturate the core? Well, if we just follow this, B is mu H, and at this point we have H is what? B over mu, so H is B sat over mu. That's the value of H sat, or the magnetic field that saturates the core. So if the magnitude of H is less than H sat, then we get this. If the magnitude of H is greater than H sat, then we saturate. And for in the positive side here, B is equal to B sat. And on the negative side here, B is minus B sat. So the core material will be not saturated or unsaturated as long as the H field is less than this amount. Now we previously had that N times I is equal to HLM. So no saturation when H is less than H sat. So that would be when I is less than H sat LM over N. And you can plug this H sat in here into there to see what value of current will saturate the core. But if the current is less than that amount, then the core doesn't saturate, and we're working on this part of the curve. Okay, so here are all the equations. Faraday's law, Ampere's law, and B is mu H, or the BH characteristic. So let's take the case where we don't saturate. So we'll use this one, and we'll plug this into here. So what we can do is use B is mu H, and plug that in here. So V is NAC times mu dH dt. And then we can use the Ampere's law equation to replace H with I. And if you do that, so we'll replace H with NI over LM, then we get this. And that's the terminal equation of the inductor. Okay. And what it says is that V is equal to this collection of constants times di dt. So it's an equation of the form V is L di dt, and apparently L is the collection of constants here. So it follows the equations of an inductor, and here's the value of the inductance. Now look at the other case. Suppose that the core saturates. So I is greater than this I sat, or saturation value. In that case, B is constant, so B is equal to B sat. And if you plug B sat into here, the derivative of B sat, the constant, is 0, and so we get 0 voltage. So when the core saturates, the voltage goes to 0, and our inductor turns into a short circuit. Sometimes we can use that to our advantage, but usually we don't like our inductors to turn into short circuits, and so we want to avoid saturation. Okay, so we've explored the basic magnetic relationships and used them to solve for the terminal equations of an inductor. We used Faraday's law to relate the flux density to the winding voltage. We used Ampere's law to relate the magnetic field H to the winding current. And we have the related quantities total flux and magnetomotive force. And then we use the BH characteristic to relate B to H and thereby allow us to solve for the relationship between V and I. With magnetic circuit analysis, we take advantage of the duality between electric fields and their equations and magnetic fields. What we're going to do is to develop equivalent circuit models for magnetic elements that look a lot like electric circuits and can be solved in a similar way. Let's consider here a magnetic core or some other similar piece of magnetic material that has some flux phi flowing down it through the material. The material has some dimensions, so there's a length L and there's some area AC. We think of this as being a magnetic conductor, which is similar or analogous to an electrical conductor. So here, instead of voltage, we have magnetomotive force across this element. That magnetomotive force drives a flux through the element. So these are the analogs of voltage and current. And the element itself is a conductor of magnetic field. From the previous lecture, we found that with a uniform magnetic H field, H, down an element, there's a total magnetomotive force, F, equal to H times the element length. More generally, it's the integral of H down the element, but if H is constant, then we get this. We can also talk about the B field, or flux density, in the material. It's related to the total flux phi by integrating flux density over the area. So if we have some area AC and we have a constant flux density B, what we get is that B is the total flux phi divided by the area. Finally, we have B as mu H, or H is B over mu. Let's substitute magnetomotive force, which is H times L, with H as B over mu. So B over mu is H times the length. And then B is the flux, total flux over the area, so we get total flux times length over the area times mu. And finally, we can write this as that magnetomotive force is equal to flux times this collection of constants. That's the length over the area times mu. This collection of constants is what we call the reluctance of the material. It's a lot like the resistance of a conductor. And so we have the magnetic analog of Ohm's law, which is the magnetomotive force is the flux times the reluctance for some magnetic element. What we will do is draw a magnetic circuit element here that looks like a resistor, looks like an electrical circuit. It has a magnetomotive force F across it. We will represent the reluctance with a symbol that looks like a resistor, and the current through it becomes the flux through the element. So if we have some magnetic structure that has different elements in it, say there's multiple windings, there's air gaps, there are cores with different dimensions, we can represent each element with a reluctance, such as the one on the previous slide. We found in the last lecture that windings are sources of magnetomotive force from Ampere's law. So we can represent each element in this way, and then what we get is a circuit model that we can solve with standard circuit analysis. Okay, there are actually magnetic analogs of Kirchhoff's laws, and they come from Maxwell's equations. The analog of Kirchhoff's current laws, where we have a node, say some node, and the node equation says the sum of the currents into the node equals 0. The analog of that is the sum of fluxes into a node equals 0. And the reason for this is that flux lines are continuous and they can't just end. So one of Maxwell's equations is divergence of B equals 0, and that's what it says. So if we have a magnetic circuit, we can have some node, and the sum of fluxes into the node equals 0, just like Kirchhoff's current law. Kirchhoff's voltage law comes from Ampere's law. Kirchhoff's voltage law says the integral of H dot dl around a closed path is the total current through the interior of the path. This is basically the sum of MMFs around a closed loop, around a loop. And it adds up to 0 as long as you view the currents as being sources of MMF. So let's do an example. Let's say now we have an inductor that has a core with uniform cross-sectional area, except it has an air gap right here. And so in the air gap, the permeability is different. We have mu naught for permeability there. And then we have a winding with N turns of wire. Okay, so what is the magnetic equivalent circuit for this? Well, we have the winding as a source of MMF. There are N turns of wire carrying current I. So the MMF here, which is the sum of the currents flowing through the interior of the path, is N times I. And we have an MMF source, looks like a voltage source, to represent the winding current. Then we have a core, and we'll take the core material, we'll assume it's uniform all the way around the core, from one side of the air gap to the other around the core, and that has some reluctance. Okay, the reluctance is what? It's the length of the element. So let's take the length. I'm going to define L core is the distance from once, that the flux takes going around the interior of the core from one side of the air gap to the other. Okay, and then we divide by the area. Let's assume the core has some constant cross-sectional area, A sub c. And then we divide by the mu of the core. And finally, we have an air gap. Okay, so the air gap is we can treat as another element in the magnetic circuit. It has its reluctance. We'll define that as R gap. The reluctance of the gap is a similar formula. It's the length of the gap, so this distance, divided by the cross-sectional area. Let's assume the cross-sectional area is the same as the area of the core. Actually, fringing flux will make it effectively the area a little bit larger, but let's ignore that for now. And then the mu of the air is mu naught, the permeability of free space. So we have an equivalent circuit, and we can directly write the elements just like this. Finally, the flux in the core, I'll label that, is the flux around this circuit. And what happens is the magnetomotive force, or Ni, source drives flux through the reluctances of the core and the air gap. Here's the model I just derived with the reluctances. And finally, what we can do is solve the circuit. So what we have from just solving the circuit is the voltage over the resistance, or MMF over reluctance, equals the flux phi. Basically Ohm's law. Finally, let's solve. Here's what we had from the last two slides. We've solved for the relationship between current and flux. The last thing we need to do to get the terminal equations is to find the relationship between the voltage and the current of the winding. So we have current here in this equation. We need to get voltage. And if you recall from the previous lecture, the relationship between voltage and flux is given by Faraday's law, that the voltage induced in each turn here from Faraday's law is d phi dt. So the total voltage, V, is d phi dt in one turn. There are N turns that each have the same flux phi in them, So each turn will have the same voltage, and the total voltage of the winding will be N times d phi dt. So we can plug that into here, or really plug this, solve this for phi and plug it into here. What phi would be Ni over the sum of the reluctances. Plug that into here, so V is N times d phi dt. The derivative of this will have another N, so N squared times di dt, and we divide by the reluctances. Okay, so we have an equation of the form V is some collection of constants times di dt. We can recognize this is the form of the equation of an inductor, and apparently this is the inductance. So V is L di dt, and there's what the inductance is. It's N squared over the sum of the reluctances. Okay, it's interesting now to look at what the air gap does. People put air gaps in inductors. Why would you do that? So if we look at our equation for inductance right here, what is the effect of adding the air gap? Well, it adds additional reluctance to the denominator, which would reduce the inductance. Well, why would you want to do that? So there are several reasons for this. One reason is that it makes the inductance less dependent on the core reluctance. And one thing about cores, magnetic cores, is that the mu of magnetic cores often is a strong function of things like temperature and can have variations, whereas the mu of air, mu naught, is a fixed number. So it's possible here to make more stable inductors whose value doesn't change as much with things like temperature by adding an air gap. So we sacrifice some inductance, but what we end up getting is a more stable value of inductance. There's a second reason for this as well, which is saturation. So last time we saw that cores can saturate. We have a saturation flux density B sat of core material, and so there's a flux that corresponds to that. So there is a value of total flux that makes the inductor saturate. Okay, let's plug this phi sat into here to find the current at which the core saturates. So I'll call it I sat. It would be equal to phi sat times the sum of the reluctances. And we can simplify this, and what we get is this equation, which gives the value of winding current that makes the inductor saturate. And what you can see is that by adding air gap reluctance, you make the value of I sat increase. So for a given core that has a given reluctance, has a given cross-sectional area, B sat is a function of the core material that is given. What we can do by adding the air gap is to increase the current at which the inductor saturates. So we're trading off inductance for saturation. Often you'll see plots here that look like the BH loop. We've actually multiplied B by cross-sectional area to get flux, and H is proportional to Ni. So when we plot Ni versus phi, we get a curve that has a shape similar to that of the BH loop of the material. And what we're doing is we're reducing the slope by adding in reluctance, but we're increasing the saturation current of the inductor. So to summarize, the magnetic circuit approach is a pretty simple way to model more complex magnetic structures and to see the effects of things such as air gaps and inductors. And we can extend this further to more complicated systems such as coupled inductors or transformers, which we'll do in the near future. Let's consider now a two-winding transformer. Here we have a core that has two windings on it. We have polarity marks shown here, the dots, and what these denote is the relative directions of the currents in the two windings. Here we have current I1 that flows into the window or the hole in the middle of the core. And likewise for the second winding, we have a current I2 that flows in the same direction downward through the window of the core. So if we have flux phi that flows around the inside of the core, then we can use Ampere's law on this flux to say that the integral of H dot dl around the core, which is the magnetomotive force in the core, is equal to the sum of the currents passing through the interior of the path, or in this case the sum of the amp turns of the two windings, N1 I1 plus N2 I2. The magnetomotive force around the core, or around the path, can be written as the flux times the reluctance of the core, where the reluctance of the core, as usual, is the path length of the core material, the distance all the way around, divided by the mu of the core and the cross-sectional area of the core. So then Ampere's law gives us this basic equation, and we can write an equivalent circuit model that goes along with it, where the flux times the reluctance is the magnetomotive force across the core, and that's equal to the sum of the amp turns of the two windings. So we can write a total equivalent circuit like this, and note the polarities of the MMF sources. They add as we go around the loop. Let's construct an electrical equivalent circuit model now to go along with our magnetic circuit model. The simplest version gives us the ideal transformer. And in the ideal transformer, the reluctance of the core tends to 0. So in this case, if this reluctance goes to 0, then the magnetomotive force also goes to 0. And what we have is that the sum of N1 I1 plus N2 I2, the two sources, add up to 0, like this. This is the equation then of the terminal currents of the ideal transformer, and it says that the currents are related by the turns ratio. We can also model the voltages, and to do that we use Faraday's law. So we have a flux phi that passes through the interior of the windings, and in the ideal transformer we assume that it's the same flux in both windings. So it's the flux phi, which induces a voltage by Faraday's law in the first winding of N1 d phi dt. And in the second winding it will likewise induce a voltage of N2 d phi dt. And the key point here in the ideal transformer is that the phis are the same. So we have the same flux linking both windings. So we can actually then eliminate d phi dt. So d phi dt from the first winding would be equal to V1 over N1. And in the second winding, d phi dt is equal to V2 over N2. So since it's the same flux, then Faraday's law tells us that the voltages are related according to the turns ratio as well. So then we get these equations for the ideal transformer, and they come out of the magnetic circuit model for the case when the reluctance of the core goes to 0. These equations we commonly relate with the ideal transformer, or model electrically with the ideal transformer. Next, let's add back in the reluctance of the core. So let's suppose the core reluctance is not 0. In that case, we can't leave this term flux times reluctance out of the equation. So what we can do instead is use the Faraday's law equation that we just derived and solve this first one for flux and plug it into the second one to eliminate phi. So the flux then would be equal to the sum of the amp turns divided by the reluctance. We can plug that into here, and we would get that V1 is N1 times the derivative of this flux. So that would give us N1 di1 dt plus N2 di2 dt. What I've done in the next equation on the slide is simply to pull out the N1, pull this N1 out, and what we get is this. So the voltage V1 is related to this effective inductance, N1 squared over the core reluctance, times the derivative of a sum of two current terms. So we can write this in the form that V1 is an effective inductance that we call the magnetizing inductance Lm, times the derivative of this effective current, which we call the magnetizing current Im. Where are those inductances and currents in the equivalent circuit? Here's the ideal transformer from the previous slide, and if you look at it, we have current I2 flowing into the secondary dot, and so we'll have flowing out of the secondary dot I2 times the turns ratio, so N2 over N1 I2. That current is this current. The other current, I1, is the primary current, and the sum of the two currents actually looks like a node equation. It's this current that we define as Im, the magnetizing current, and it's flowing through a magnetizing inductance Lm that is given by N1 squared over the core reluctance. So when we include the core reluctance as a non-zero quantity, what we get is an effective inductor called the magnetizing inductance that is in parallel with the winding. You can actually draw the inductor on either side of the ideal transformer. We could push Lm through the transformer, turns ratio squared, and on the secondary side write this as N2 squared over the reluctance. The magnetizing inductance is a real inductor. It models the magnetization of the core. So for example, we could do the thought experiment where we just disconnect the secondary and connect the primary up into our circuit. What would we expect to see? Well, with just the primary, we have some turns of wire on a core, and that makes an inductor, and the inductor is in fact the magnetizing inductance. The equivalent circuit reflects that. If you disconnect the secondary of the ideal transformer, then we have an open circuit on the primary side, and effectively the model reduces down to the magnetizing inductance. This is a real inductor also. It has saturation and hysteresis, which is in fact coming from the actual core material. You can saturate the transformer then by saturating the magnetizing inductance. So if the current in the magnetizing inductance becomes too large, it will saturate the transformer. The magnetizing inductance will turn into a short circuit, and that'll short out the windings of your transformer. The one other thing the magnetizing inductance does is it causes the currents to differ from the turns ratio. As I mentioned a minute ago, the transformer will saturate when the magnetizing current becomes too large. However, this is not the same as saying the transformer saturates when the winding current is too large, because the winding currents can differ from the magnetizing current. In fact, if we put a large current in the primary and it all comes out the secondary with no current flowing through the magnetizing inductance, the transformer doesn't saturate. We generally don't think of transformers as saturating because the winding current is too large. Rather, we think of them as saturating when the applied volt seconds are too large. In fact, we can bypass the magnetizing current altogether and simply go to Faraday's law, where if we integrate Faraday's law to get the flux density in the core, it's given by 1 over the turns times the cross-sectional area times the integral of the voltage, and the current doesn't really come into play. So if you apply too many volt seconds to the winding, then you will make your transformer saturate. So we think of transformers as saturating based on applied voltage rather than the applied winding current. We saw previously in the last lecture that if your inductor is saturating, you can fix that by removing turns or adding an air gap. In the case of the transformer, neither of those work, and in fact what we need to do is reduce the flux density in this equation. To do that, you add turns. So make N1 larger rather than smaller, and that will tend to make your transformer stop saturating. Okay, so we saw that the magnetizing inductance causes the winding currents to differ from the turns ratio. The voltages can also differ from the turns ratio, and this happens from a phenomenon called leakage inductances. So to relate the voltages in the ideal transformer, we assume that we had the same flux passing through the interiors of both windings. Here in this drawing, that's called the mutual influx phi sub m. But in practice, there can be fluxes that pass through one winding and not the other, and these are called leakage inductances. Here I've drawn some fluxes that we say leak out of the core into the air. And the bottom line here is that this is flux that passes through one winding and not the other. So in this case, when we write Faraday's law, V1 is N1 times the derivative of the flux passing through the interior of the winding. That flux in this case, is drawn here, is a sum of leakage flux, VL1, plus the mutual flux, Vm. And V2 likewise is N2 times the derivative of a leakage flux VL2 plus the mutual flux Vm. And the point here now is that the leakage fluxes cause the voltages to differ and no longer scale according to the turns ratio. Really, this case, as drawn here, is topologically equivalent to having separate little inductors in series with each winding, and those inductors carry the flux. So this term here effectively looks like an inductor with N1 turns carrying flux VL1, which I've just drawn as a separate core, and similar for winding 2. So these things look then effectively like series inductors. The voltage drops across those series inductors then will cause the voltages, the terminal voltages, to differ. So here is an equivalent circuit that includes the leakage fluxes. So we have a magnetizing inductance and then we have two leakage inductances. This is the well-known T model of the transformer. It contains 4 parameters. There's a magnetizing inductance or a mutual inductance. There are 2 leakage inductances and there's a turns ratio. Now we know from basic circuit theory that you can write the terminal equations of a 2-winding transformer with this matrix form, where this is called the inductance matrix. And the inductance matrix turns out to have 3 independent parameters. L11 and L22, which are called the self-inductances of the primary and secondary windings, and then L12, which is the same. It's the off-diagonal term, and it turns out by reciprocity that it's the same term in both cases here. So the inductance matrix in general has 3 independent parameters rather than 4, and in the equivalent circuit model of a 2-winding transformer, there are 3 independent parameters, and the 4th can be chosen arbitrarily. A common case is to choose the turns ratio here as the physical turns ratio of the transformer winding, and then solve with measurements to find the inductances, the 3 inductances of the T model. The T model parameters can be related to the inductance matrix with these relationships. It's common in circuit theory to also define an effective turns ratio, which is defined to be the square root of the ratio of the self-inductances. This is a parameter that may not be the same as the actual physical turns ratio of the transformer. This effective turns ratio is based on the elements in the transformer model. We also can define a coupling coefficient. The coupling coefficient is a measure of how closely or tightly coupled the two windings are. As the coupling coefficient tends to 1, the leakage inductances go away and tend to 0. Good transformers will have coupling coefficients slightly less than 1. In a typical switching converter, it's not uncommon for half the loss to be in the semiconductors, for example, switching loss and conduction loss, and the other half of the loss, more or less, to be in the magnetic elements. In this lecture, I'm going to introduce the mechanisms that cause loss in magnetic elements. We're going to start by talking about the core loss caused by the hysteresis in the BH loop of the device. We'll talk about the loss caused by the DC resistance of the wire. Then we'll talk about AC effects that come from the skin effect and from eddy currents, which can cause increased copper loss in the windings and increased core loss in the core material. So let's talk first about core loss. Classical core loss is manifested in the hysteresis characteristic of the BH loop of the magnetic material. To find the effect of this, we can integrate the power flowing into the inductor winding to see how much energy is lost over a period, say a switching period. So if we have a winding that has a voltage applied and a current, then the power going into the winding, P of T, of course, is the voltage times the current. Let's assume that these are periodic waveforms, so we can integrate P of T to find the net energy that flows into the winding over one cycle. And I'm going to call that energy W, and we will integrate over one cycle this power. If the inductor is ideal, then we expect no loss, and this integral should turn out to be 0, but losses then will cause this to have a positive value. So let's substitute V and I using our relationships from Faraday's law and Ampere's law to relate V and I to the B and H inside the core. So from Faraday's law, we have V is NAC dB dt, where N is the number of turns and AC is the cross-sectional area of the core. Okay, so there's V. And then I is given by Ampere's law. So here I haven't written an air gap or anything. Let's just assume it's a uniform core. So what we got from Ampere's law was H times the magnetic path length is equal to the turns times the current. So from this we can solve for current. I of T is H of T times the path length over the number of turns. So we'll plug that in for I. And then we integrate dt. Okay, let's see, we can cancel some things. So the n's cancel. This turns into dB. I can pull the constants AC and LM out. So this goes to AC times LM times the integral over one cycle of what? H dB. And that's written again down here. Okay, let's look at this. What is AC times LM? Well, AC is the cross-sectional area, and LM is the path length, or the distance around the core. AC times LM, then, is actually the volume of the core material. Okay, so we have volume of the core, and then multiplied by the integral of H dB. Well, this integral over one cycle is in fact the area of the BH loop. To integrate h dB over one cycle, let's see, dB, B is on the vertical axis, so we're actually integrating this way. Let's start, say, down here and go around the BH loop once, so over one cycle of the AC. So the integral of h dB is this area. First, as we go up the BH loop, all the way to the top, or however far we go. And that's over the first half cycle. Then over the second half cycle, we go down the other side, the left side of the BH loop. Let me change colors here and draw that. So going down the left-hand side, when we integrate, we get an area that goes just to the left side of the BH characteristic. And for this second half of the cycle, dB is negative. We're decreasing B where we were increasing it before. So this total integral or area is the blue area minus the red area. And what we get, in fact, is the difference, which is the area of the BH loop. So the answer here then is that the energy loss per cycle is the volume of the core multiplied by the area of the BH loop, and this is the net area that's traversed over one cycle. So hysteresis then leads to core loss. When we go up the right-hand side of the BH loop, we're storing energy in the magnetic field. When we go down the left-hand side, we're recovering energy, but we're not getting it all back because of the hysteresis. Okay, this is the energy loss per cycle. If we do this at some frequency, then the power, or energy loss per second, is the energy loss per cycle times the cycles per second, or the frequency. The power loss then, or we call it the core loss, is the frequency multiplied by the core volume multiplied by the area of the BH loop. So hysteresis loss then varies directly or linearly with the applied frequency, although what you might see in practice, if you actually build an inductor and are able to measure the BH loop, you may see that when you turn up the frequency, the area of the BH loop looks like it increases. And so then, in fact, you get more energy loss per cycle at higher frequencies. Charles Steinmetz, around 1900, was a well-known, famous engineer at General Electric laboratories, and he developed some empirical equations for core loss that we now call the Steinmetz equations. An early version of this is hysteresis loss, which was this formula that he used. He said hysteresis loss is equal to some constant multiplied by the frequency of the AC and then multiplied by the maximum flux density to some power alpha, where alpha is an empirical parameter that we fit to the curve from experimental measurements. So the constant k sub h and the exponent alpha are empirically determined. Okay, hysteresis loss is not the entire story of core loss. There's a second effect that is very significant as well, called eddy current loss, and this comes from Lenz's law. The problem here is that the magnetic cores not only are good magnetic materials, but usually they are metals that are good conductors of electricity. So if we have a piece of core material, such as sketched here, and we have some AC flux passing through it, what happens is that it induces eddy currents or electrical currents that flow in the core material and its conductors, and by Lenz's law, those eddy currents attempt to prevent the flux from changing. So the eddy currents will go in a direction that makes an opposing AC flux. So what we see is significant electrical currents flowing around the core material, and those currents cause resistive losses in the core. We call those losses eddy current losses, and they are proportional to I squared times the resistance of the core. Eddy current losses are a big problem, and they cause significant loss. So the magnetics industry goes to great lengths to try to reduce the eddy currents. One way that is commonly used, especially at 60 Hertz for transformers, is to use iron laminations. So the core then is comprised of laminations or thin layers, that are sheets of core material, and between each sheet is an insulator. So what we're trying to do is break up the eddy currents from flowing. For this to work, the laminations have to be thin enough so that we don't have significant eddy currents within a sheet. And not only that, but we find at high enough frequency the capacitance between the laminations lets eddy currents flow anyway. At higher frequencies, we use powdered iron materials, where we basically take the iron material, grind it up into a powder, and then have some kind of glue or potting compound that gets it to stick together and form a solid core. So then the particles, if they're ground fine enough, will have low eddy currents, but still capacitance between particles or grains can still allow eddy currents to flow. Ferrite materials are similar. There, the ferrite material is ground into small particles that are on the order of a micron across. They're coated with an insulating material, and then they're pressed together at high pressure so that we have compressed grains of ferrite with very small size, say a micron or so. And these ferrite materials then have low eddy currents at hundreds of kilohertz. The problem is still that there's capacitance between grains, and that capacitance still lets currents flow. And as you turn up the frequency, the impedance of the capacitor becomes smaller and smaller, and the eddy currents go up quickly. In fact, if you take a piece of ferrite core material and put it on a network analyzer, say, to measure the impedance of the ferrite, it turns out to be capacitive. So as you turn up the frequency, the magnitudes of the eddy currents goes up quickly, and then I squared R goes up even quicker. So ferrites are good up to a certain extent, but sooner or later, again, we have significant eddy currents. The classic Steinmetz equation for eddy current loss is this one. This says that eddy current loss goes like frequency squared. This is true if we don't have laminations or ferrite, and we simply have a resistive core material. Where the core material is capacitive in impedance, then eddy currents go up quicker than F squared. Manufacturers' data sheets will typically give plots of core loss. Here is a typical plot, plotting core loss density in watts per volume, per unit volume, versus, in this case, the peak flux density, delta B, in Tesla. And there are curves for different operating frequencies. Generally, these are with sinusoidal excitation. Also notice that this is plotted on a log-log scale, so a straight line on these axes is a function that goes like delta B to some power, where the power or exponent depends on the slope of the line. In fact, you can fit a formula to one of these lines. That formula will have this form where it varies as delta B to an exponent, where again the exponent depends on this slope. There's a constant, and then we have the volume to get the total power loss. Functions of this form today are routinely called Steinmetz equations. I mentioned these different types of materials. Iron laminations or silicon steel are commonly used in low frequency applications, such as in the utility system. The saturation flux densities of these materials typically are around 1.5 to 2 Tesla. but they have relatively high core loss. At higher frequencies, say 1 kilohertz transformers or maybe 100 kilohertz filter inductors that have small ripple, we see powdered iron, polypermalloy, and similar kinds of cores used. These have less core loss than the laminations, and they have lower saturation flux densities, typically 0.6 to 0.8 Tesla. And then at even higher frequencies, we see ferrite used quite commonly. Manganese zinc is typically used at 100 kilohertz to a megahertz. Nickel zinc is useful at higher frequencies. These typically have saturation flux densities of 1/4 to 1/2 of a Tesla, and we use them all the time for our switching converter transformers and filter inductors. In addition to core loss, copper loss is a significant non-ideality in our inductors and transformers. And to first order, this is simply the resistance of the wire used to make the winding. In earlier courses, we've modeled this DC copper loss of our inductors with our equivalent circuit models. Here we'll talk about how to actually calculate that resistance. Simple equation for resistance of a wire, this is the DC resistance, R, is the resistivity of copper, rho, times the length of the wire, LB, divided by the cross-sectional area of the wire, AW. The resistance of copper at room temperature is quoted as 1.724 times 10 to the minus 6 ohm centimeters. This resistivity is a function of temperature, and it increases as temperature goes up. At 100 degrees C, the resistivity is approximately 2.3 times 10 to the minus 6 ohm centimeters. So if we put a current in our winding, we get copper loss equal to the RMS current squared times this resistance. The DC copper loss is important, but at the 100 kilohertz and higher switching frequencies of our converters, the skin effect effectively increases the resistance of the wire so that we have an AC resistance that can be significantly higher. The skin effect comes from Lenz's law. So what happens is if we put a current through a wire, the current makes a magnetic field, and so by the right-hand rule, if we have a current, say going from left to right here, we'll get a flux that goes around that current or goes around the wire in the clockwise direction. And that flux induces eddy currents in the wire that attempt to oppose changes in the flux. And by the right-hand rule, we can sketch what those eddy currents do. So here's a little sketch of these ovals are the induced eddy currents. And if you look at this, just in the directions that they flow, the eddy currents oppose the current in the middle of the wire, and they increase the current on the surface. This is the origin of the skin effect. With a large enough conductor and a high enough frequency, the eddy currents will push the current out of the middle of the conductor and make it all flow on the surface, on the outside. Basically, the conductor rejects flux from changing in its center. It pushes the magnetic flux out of the wire, and it makes all of the currents flow on the surface of the wire. We could solve Maxwell's equations in the wire, and when we do, here's what we find. For a sufficiently large wire, the current density is a decaying exponential function of the distance into the wire. So that the current density, I'll call it J, is some constant times a decaying exponential function, e to the minus x over delta, where x is the distance into the wire and delta is called the skin depth. From solving Maxwell's equations, we can find what this characteristic value or skin depth is, and it turns out to be the square root of the wire resistivity divided by pi, 3.14, times the magnetic permeability of the wire, which usually is mu naught, and the frequency. So if we plug in numbers here for copper at room temperature, this turns out to be 7.5 centimeters divided by the square root of the frequency in hertz. And here's a plot of that on a log scale. So this is the skin depth here in centimeters, and this is the frequency. So for wire at room temperature, or 25 C, here's what we get. At 100 kilohertz, the skin depth turns out to be 0.02 centimeters, or 0.2 millimeters. So it's pretty small number. On the right-hand side, for reference, I've compared this to standard American wire gauge values. And a wire that has a diameter of 1 skin depth at 100 kilohertz right here is about number 33 gauge wire, which is pretty small wire. Normal hookup wire in the lab is 20 gauge. What we wire our house with is 10 or 12 gauge, so it's up here. Much bigger wire. This kind of wire, 33 gauge, can't carry much current. The skin depth is significant in our 100 kilohertz converters, and if we want to use wire that can carry multiple amps, so that the wire size is way up here on the scale, our wire is very thick compared to the skin depth. What is the effective AC resistance of a wire that is much thicker than 1 skin depth? Let's go back and look at this plot showing this decaying exponential current density going into the surface of the wire. We can take this decaying exponential current density and integrate to find the total resistive loss in a wire that has current density varying like this. And the answer to that is it turns out to be the same as if we just had a hollow tube whose walls are the thickness of 1 skin depth. So it's like we hollow out the conductor, throw out the inside part, and just have maybe a pipe or tube or cylinder that is 1 skin depth in thickness. And if you calculate the DC resistance of that, and to get the effective resistance, we call that the AC resistance, it turns out that you get the correct answer with a uniform current in such a hollow tube. So the impact of the skin depth is to greatly increase the effective resistance of our conductors. Now, if the skin depth were the only problem, perhaps we could deal with it, but there's an even worse problem that is a corollary of the skin depth, and it's called the proximity effect. The proximity effect is what happens when you place conductors next to each other. Current flowing in one wire will induce eddy currents in the nearby wire. Here's a simple case where we have a conductor, conductor number 1, that has current I flowing in it. So there's total current I flowing in this conductor. And then we place a similar conductor next to it that has 0 current flowing in it. So normally we would expect conductor 1 to have some resistance or some power loss that would be the RMS current squared times the AC resistance, accounting for the skin effect. So this conductor will have all of its current flowing on the surface, and it's effectively a sheet of copper that is 1 skin depth thick, and it induces this loss. What happens when we place another conductor next to it is that this current I flowing through conductor 1 induces an equal and opposite current on the surface of conductor 2. Basically, the current I on the surface of conductor 1 has a magnetic field that will flow around this conductor. That magnetic field attempts to penetrate conductor 2, and it induces eddy currents on the surface of conductor 2 that reject that magnetic field to keep it out of the conductor. So if these conductors are close enough to each other, we will get an equal and opposite current on the surface of conductor 2. So I've drawn minus I here. And that current minus I will have loss as well, that is I RMS squared, the RMS current squared, times the AC resistance for conductor 2, which we can assume it's the same resistivity and the same AC resistance. But conductor 2 has no net current flowing. If there's no net current, how can we have current I in the opposite direction on the left surface of conductor 2? Well, the solution is that we have current flowing in the opposite direction on the other surface of conductor 2. So there's minus I on the left side, plus I on the right side, and the net current in conductor 2 is 0. But the right-hand side has another amount of copper loss, another RMS current squared times AC resistance. And so what we get is a net 3 IRMS squared RAC as the total copper loss in this situation. The current in conductor 1, which itself has this much loss, induces twice that much loss in the next conductor over, in conductor 2, and we get a total of 3 times the copper loss. The problem with the proximity effect is that currents can increase geometrically when we have many layers of windings and multiple conductors together on a core. This was a quick introduction to the proximity effect. In upcoming lectures, we'll cover this in more detail and work some examples. So our magnetic elements have hysteresis and eddy current loss in the core. They have DC copper loss, and then they have AC copper losses in addition coming from the skin and proximity effects. When we design our magnetic elements, we need to account for all of these effects to minimize loss and optimize our design. Section 10.4 is about AC losses in winding conductors through the mechanisms called the skin effect and the proximity effect. These AC losses in the windings can be one of the largest sources of loss in a switching converter, and often the transistor switching loss and the magnetics proximity loss are the largest sources of loss and inefficiency. Let's talk first about the skin effect. This comes from eddy currents and Lenz's law in Maxwell's equations. So let's suppose we have, say, some round copper wire or cylindrical wire, and we put an AC current I of t through it in this direction. Maxwell's equations tell us that there will be magnetic flux around this wire, and by the right-hand rule it goes up and over and around like that. So there's a magnetic flux phi of t induced by the AC current I of t. And it's drawn here inside the wire. So if we have current flowing inside the wire, there will be magnetic flux inside the wire. Now, just as in the core loss, or eddy current loss inside magnetic cores, we have similar kind of eddy current loss inside the winding conductors. And what happens is that this magnetic flux induces currents in the conductors, and the currents align in a way that tend to oppose changing flux, and ultimately they end up opposing the changing current. So we see them going around in small loops like this. A cross section is drawn over here, and you can see that the eddy currents tend to cancel out the current in the middle of the wire, while they tend to reinforce or increase the current on the surfaces. We can solve Maxwell's equations. I'm not going to take the time to do it here, but we can solve Maxwell's equations to find how the current actually distributes itself inside the wire under these AC circumstances. And what we find is that the current density in the wire is a decaying exponential function of the depth or distance into the wire from the surface. So say we have a plot here, I'm going to plot a distance x into the wire versus current density J, and this function right here is some function that goes like e to the minus x over delta, where the characteristic length delta is called the skin depth, or the penetration depth. Okay, so we have a decaying exponential function for current density versus depth into the wire. In other words, what happens is that the current crowds at the surface of the wire, and if we have a wire that's much thicker than one skin depth, then there's very little current flowing in the middle of the wire. What we're interested here is in the effect of this on the loss in the wire, or what we call the copper loss. So if we had the DC case, where we just have a constant DC current I, and we have a copper wire, then we can write that the copper loss is the current squared times the DC resistance, and the DC resistance follows the classic formula that it's the resistivity of the wire, rho, multiplied by the length of the wire, divided by the cross-sectional area of the wire. In the case of AC currents, the skin effect, which causes the current to crowd at the edges, effectively increases this resistance. And so we talk about an AC resistance of the wire that tells us the copper loss with an AC current, say a sinusoidal AC current flowing in the wire. With sinusoidal currents, we can write this as the RMS current squared times this effective AC resistance. And we can talk about the AC resistance following a similar kind of function, the resistivity times the length divided by some effective cross-sectional area of the wire, but the cross-sectional area of the wire effectively is smaller because the current is not flowing down the middle of the wire. It can be shown really by integrating the current density function squared times the resistivity. We can show that the AC resistance, or this effective cross-sectional area of the wire, is given by really an annulus. It's like we have a hollow copper pipe instead of wire. It's as if the current is just flowing on the surface of the wire, or we have a copper pipe with a thickness that's equal to the skin depth, and it's hollow in the middle. So this effective cross-sectional area, one can show, is the area of this annulus, or the copper part of this hollow pipe, having a thickness of one skin depth. So then we can talk about the AC resistance as being equal to the DC resistance times the ratio of these effective areas. The skin depth delta can be shown, again by solution of Maxwell's equations, to be given by this expression. It's the square root of the resistivity of the wire, rho, divided by pi, and the permeability, mu, of the wire. The permeability of copper is basically mu naught, the permeability of free space, and then also times the frequency in hertz. So for copper wire at room temperature, if we evaluate this expression, it turns out that the skin depth is 7.5 divided by the square root of the frequency in hertz, and this is in centimeters. Here's a plot of that versus frequency. So we often build switching converters with switching frequencies of maybe 100 kilohertz or a megahertz or something like that. Here's what this formula predicts for the skin depth. And we're getting skin depths that are, less than a millimeter at 100 kilohertz, and room temperature, the skin depth is about 0.2 millimeters right here. And so it's pretty small. In fact, if we compare it to wire sizes, a wire that has one skin depth of diameter at 100 kilohertz is about number 33 gauge wire. This is American wire gauge. 33 gauge wire is pretty small. You usually wouldn't put more than maybe 1/10 of an amp or so through that. If we have larger currents, amps or tens or hundreds of amps, where we have much larger wires that are maybe up here on this scale. So these wires have diameters much, much greater than 1 skin depth. So the skin effect is very important. In fact, it's even important at utility frequencies, 60 or 50 hertz. Of course, the skin depth is larger, but you know, skin depth is just a weak function of frequency. It goes like square root. Plus, often at these utility scale applications, we have very large currents. And so we have large conductors that are even larger than this. They're big conductors, and the skin depth even, or skin effect even at 60 hertz can be important. So the skin effect increases the copper loss, and we have this effective AC resistance that can be much larger than the DC resistance. Now, if that were the only problem, we could probably deal with it, but actually there's an even worse thing that happens that is called the proximity effect. The proximity effect we can think of as a corollary of the skin effect, and it's what happens when you have adjacent conductors that have AC currents, and they interact with each other. For simplicity, I'm going to draw the conductors as square instead of round now, and we're not going to worry about the effect of round wires. We'll come back to that later. But we can think of, say, a square or rectangular cross-section wire that is going in and out of the page here. And it has some thickness, h, that is much greater than a skin depth. So let's consider what happens when h is much greater than the skin depth delta. Okay, and this conductor 1 here, has current I flowing down it. And so we know from the skin effect then that the current density inside this wire is this decaying exponential function of depth into the wire. And so we have some function like this for the current density. And that current, I've drawn it here, is coming out of the page. By the right-hand rule, we'll have flux going around the wire like this. And now let's consider what happens if we bring a second conductor up next to the first conductor. And let's say our second conductor has no current at all flowing in it. So net current of 0. Well, what happens when you put the wire this second conductor next to the first one is that this magnetic field induces eddy currents in the second conductor. And in fact, if we have the same flux phi on the surface of the first conductor, also near the surface of the second conductor, we'll get the same kind of current distribution. So in fact, there will be current on the second conductor that flows in a way to try to cancel out the magnetic field by Lenz's law, or oppose changes to the magnetic field. And so the current on the surface of this second conductor will flow in the opposite direction. So it'll go into the board in the opposite direction of the current in the first conductor to try to cancel the magnetic field out. So we get an equal and opposite current on the surface of the second conductor. Now, the second conductor has no net current. Yet if we have current I flowing out of the board, we must have some opposite current somewhere in the second conductor so that the net current in the second conductor is 0. And what happens is that we get this return current flowing on the other surface, the opposite surface of the second conductor. So we have current circulating into the board on the left side and out of the board on the right side of the second conductor. There is no net current in the conductor. They add up to 0, but we have current circulating around the second conductor. How much power loss is here? Well, the first conductor has a power loss, call it PCU1 for the power loss in the first conductor, and that's equal to the RMS current squared times the AC resistance. that we talked about previously. The second conductor has two of those. It's got this equal and opposite current on one surface and an equal magnitude return current on the other surface. And so PCU2, the second conductor, really has two of these. So there's a net copper loss now of 3 times. So the increased RAC comes from the skin effect, and now we have this factor of 3 that is coming from the proximity effect. So our copper losses are going up fast. Okay, let's think about a transformer. So let's suppose we're trying to build a transformer that has a primary and secondary winding, and let's say it's 3 turns to 3 turns, and we have current I, say, flowing in the primary, that's AC, and so we'll have a secondary current going in the opposite direction that is also I. Okay, here I've drawn a structure with a magnetic core and then with some turns inside of it. Okay, let's talk for just a minute about how we do that. Here is what's called a ferrite PQ core. It has a magnetic core, a ferrite core, and then inside of it there is a bobbin. It's a plastic bobbin with some pins that let you put it into a printed circuit board. And we wind wire on the bobbin, and then we get the windings on the core. So here's what the core halves look like. There's a round center post and then some outside posts, and the magnetic flux will go down the round center post and then out the outside posts. Okay, the bobbin fits inside the core, and what you do is you take your copper magnet wire and you wind it on the bobbin. So you wind your turns like this, and then you put it inside the core. So what I'm trying to draw here really is just one part of something topologically equivalent to that. So our primary winding is, say, 3 turns. Our first turn goes around the core, so I've got it going around this way. Comes to the second turn, which is put on top of the first turn, goes around this outside leg, goes to the third turn, and so on. So really we have turns going around this center leg of the core. The secondary layers are then wound on top of the primary layers, so they go around as well. So what we're drawing here is a cross section, really, of the winding. Okay, so in a transformer then, our primary turns or layers will have, say, current I. Our secondary turns will have opposite current, so minus I, as drawn here. Okay, what happens with the skin and proximity effects? So let's start with the first turn, or first layer. We have a current I flowing in it. It will flow on the outside of that layer with this decaying exponential function. Okay, so basically it's flowing in this right-hand side of layer 1 with a characteristic depth of a skin depth. This will induce flux on its surface. That flux will induce an equal and opposite current on the adjacent surface of layer 2. So I'm calling that minus I. But layer 2 has a net current plus I. So if we have minus I on the left surface of layer 2, we must have plus 2I on the right surface so that we get a total current in this layer of I. So there's 2I on the far side or right-hand surface of layer 2. That makes twice the flux, 2 phi, on that surface, and that 2 phi induces minus 2I on the adjacent surface of layer 3. Okay, but then layer 3 has net current I, and so it must have 3I on its opposite surface to get a net of 1I. So then there's 3 times the flux on the surface of layer 3, and that will induce minus 3I on the left-hand side of layer 3. Layer 3 has a net current of minus I, so there's 2I on the right-hand side. We'll get minus 2I in layer 2 of the secondary, and minus I on the left side of layer 1 of the secondary. So we have these currents building on the surfaces, the adjacent surfaces of the windings, from the proximity effect. Okay, let's estimate the loss. So in the first layer, we have a current I, and we'll have an effective AC resistance, RAC, from the skin effect. And so we get a total loss of IRMS squared RAC. In layer 2, we've got that same loss on the left surface of layer 2. And on the right surface, we have twice the current. So we'll have 2I RMS squared RAC on the right surface. And the total copper loss in layer 2 then is 1 plus 2 squared, so 5 times I RMS RAC. So 5 times the loss in layer 2 as we had in layer 1. The proximity effect makes the currents build up, and it makes the copper loss go up very quickly. Let's look at layer 3. The left-hand surface of layer 3 has 2I in current, so we'll get 2I RMS squared. And the opposite surface has 3I, so we'll have 3 times I RMS squared RAC there. And so that's 2 squared plus 3 squared. Let's see, 4 plus 9 is 13. So 13 times the loss in layer 3 is what we had in layer 1. So it's like 1, 5, and 13. Every time we add more layers or more, we can think of this as maybe flat copper wire or copper ribbon that's wound around the core. The loss is really going up geometrically with the number of turns. In fact, we can generalize this to say if we have layer m, lowercase m, these expressions are the RMS current squared times m minus 1 squared plus m squared, and this is the AC resistance. We can add up the losses in all the layers. So 1 plus 5 plus 13 would be 19. So with our 3-turn or 3-layer primary winding, the total copper loss then is 19 IRMS squared RAC. So we're getting big numbers here from the proximity loss. You can sum this series. If we have little m is the layer number, if we make capital M the total number of layers, so capital M was 3 in this case, we can sum the series, and this is what we get. So in the case where m is 3, this term here turns out to be 19. Let's compare this with what you get at DC. At DC, first of all, we have a resistance RDC, not RAC. And second, the number of layers or turns is capital M, and so the total copper loss at DC is the current squared times the number of turns times the DC resistance of 1 turn. So the ratio of this AC resistance to the DC resistance, we can divide this expression by this one, and we call that this F sub R. It's the proximity loss factor by which loss is increased, and it turns out to be this function. It goes like the number of turns or layers, the number of layers squared here, and so it can go up very quickly. So any currents in winding conductors can significantly increase the copper loss in the magnetics in our switching converters, and it's worth learning how to model and control these losses to understand how the skin effect and proximity effect work to design good magnetics for our high frequency converters. In the last lecture, we talked about the proximity effect and how currents in the windings are associated with flux in the air next to the winding. And we're calling this flux now the leakage flux. Multiple layers and multiple turns cause this flux to build up and induce additional proximity losses. It's possible to do things such as interleaving of windings to reduce this effect. And to understand that, we draw what are called MMF diagrams, or magnetomotive force diagrams, that describe this flux in the air surrounding the windings. So that's the topic of this lecture, and here we're going to call that flux leakage flux, and generally in a transformer that is indeed what it is. So here I've drawn a simple example. It's a core with high permeability, and we have some turns of round wire on it in a transformer. Here I've got 8 primary turns and 8 secondary turns. And again, we can think of these turns as going around the core like this. I guess this bottom turn will come back on the next layer of turns, and it'll go like that. And then there's the final turn for the primary. Then perhaps our secondary is on top of that. It actually doesn't matter which leg of the core it goes around. It's topologically equivalent, but we can just think of the secondary winding maybe as being on top of the primary, so our turns are going around like this, and then we get to the next layer and our turns continue to connect, and then we come out there. So we have really turns going around the post of the core, and this is a drawing really of a cross section of what the wires look like. Okay, so this would be a transformer example that's 8 turns to 8 turns with this simple geometry. Each piece of wire or each turn carries the same current I coming in the primary and going out the secondary. Okay, what is the flux then induced by these currents in this geometry? So in the transformer, we had an equivalent circuit that's the T model. So we have this ideal transformer that's 8 to 8. We have a magnetizing inductance, and we have leakage inductances. The magnetizing inductance models flux that is common to the two windings, or coupling the two windings, and we think of that as the mutual flux, which really is going entirely in the core. While the leakage fluxes in the windings are fluxes that link some of the turns of wire but not others. Okay, so generally we think of leakage fluxes as flowing at least partly in the air and not just being confined to the core where they link both the primary and secondary windings. This flux next to the windings that is associated with the proximity effect is in fact leakage flux. So we have, for example, current in these this first layer of primary turns, and there is flux that travels in the air adjacent to the first layer. We can model that flux as being proportional to the current in the adjacent turns. This flux is driven by the current in the windings, and in fact, with Ampere's law, we can calculate the size of this flux. So recall Ampere's law says if we consider the path a flux line takes in its closed loop, that the total MMF around that path that drives the magnetic field and drives flux is proportional to the current enclosed by the path. So if we say have some path with flux lines going this way through the air in the middle of the winding, then the MMF that drives magnetic field in that path is equal to the total current enclosed or in the air in the winding window inside of the path. So that this MMF is equal to the H field times the distance of the path. So let's suppose that the core has large permeability, much greater than the permeability of air. And what that means is that the MMF in the core is very small. It's very low reluctance. And nearly all of the MMF is in the air, driving the flux across basically the air gap, or in the air through the winding. So if we take this path right here for this flux line, basically all of the MMF is in the air, and if we say that our window has some height LW, then the MMF is this H right here times LW, and that's equal to the current inside the path. And as drawn here, we have 4 turns, each carrying current I, so this is 4 times I. Now, why did I draw the fluxes going vertically through the air? Why isn't there any going horizontally or diagonally or in some other direction? Well, let's consider a path going this way. As you can see, the net current inside that path is 0. There are 2 primary turns and 2 secondary turns with currents flowing in the opposite direction, and the net current cancels out and is 0. So because of the geometry of the winding, we don't expect to have horizontal components of magnetic field, we just have vertical components. Now, of course, there may be some little curves around the round wire and so on, which we're not going to model here. So we can talk about the MMF, which is from one side of the core window to the other, that is what drives the flux through the winding. And we can plot that as a function of the distance here, which we're going to call x. So this MMF is a function of x, and we can plot how it goes up and down, and this is called the MMF diagram. So we can see that for this path, the MMF is 4I. So really our MMF goes from 0 at this end and when we get here we've got 4, so we draw it like that. When we get to here, our path encloses a total of 8 turns with each with current I, so we go up to 8I. At this point our path includes plus 8I and then minus 4I for the center layer of the secondary winding, so we go back down to a net 4I, and then finally at the far end of the window we're back down to 0. So here is a plot of that, and what I've done here is simply sketch the conductors and what currents they carry, and directly under that I've drawn this MMF diagram like on the previous slide. And basically you just count the amount of current to the left of the point. So at any point, say right here, you count the amount of current to the left, and that adds up to the MMF. This diagram also is assuming that the current is uniformly distributed across the conductor. So if you choose a point X that's in the middle of the winding, This is assuming that the current with uniform distribution will increase linearly with x. We'll come back to that in a minute and account for the skin effect. But for now, we'll just draw it this way. Places where there is high MMF between the winding is places where we expect to have more eddy currents in the wires and where we'll have more proximity effect. Here's another example. This is a two-winding transformer, and here I've just drawn layers. So this layer I've just drawn as a rectangle. Perhaps it actually is comprised of a bunch of turns of wire, or maybe it is just one single rectangular conductor is drawn here. But what's important here is what is the total current in this layer, and that's what determines the MMF. Okay, so if we have total current I in the first layer, then the MMF diagram will go up to I to the right of the first layer. It'll go up to 2I here and 3I here, just like this. And then with the secondary layers carrying minus I, we'll go back down, and we'll have an MMF diagram like that. Now, with proximity effect, here's what really happens. We discussed this last time in the last lecture. In the first layer, all of the current in the first layer actually crowds on the right-hand surface of that first layer within more or less one skin depth of its right side surface. So in fact, if we move across this wire, there's no current enclosed in our path until we get to within one skin depth approximately of the right hand side, and after that we have this decaying exponential function for our current density according to the skin effect. So I'll draw a little decaying exponential function. So what actually happens is the MMF goes up to get to be I at the surface of the first conductor. Our MMF that drives flux across the air gap between the first and second conductors is driven by this current I, and it induces an equal and opposite current in the adjacent surface of the second layer. If we move past that to look at, say, what happens here in the middle of the second conductor, the minus I cancels the plus I, and we go back down to 0. And so in the middle of the second conductor, there is no MMF, and in fact, the second conductor has currents on its surfaces that are rejecting the current, expelling it so it doesn't flow in the middle of the conductor. And what actually happens then with the skin effect is that there is no MMF in the middle of any conductor, and we have surface currents that achieve that. So then we see 2I on the right side of that second conductor, as we discussed in the last lecture, and our MMF goes up to 2I to its right in the air gap. That gets canceled out by the surface currents on the third conductor. We have a decaying exponential down to 0, and so forth. So you could draw these straight lines, but in fact we have these decaying exponential functions, and we have 0 MMFs in the center of any conductor. Something we often do to reduce the proximity effect, and with great success, is to interleave windings. So here's an example of this same transformer with 3 primary layers and 3 secondary layers, and what we do here is we interleave the primary and secondary, so we alternate primary, secondary, like this. If you draw the MMF diagram in this case, the secondary, this first secondary, its current is equal and opposite to the current in the first primary, and we simply have the currents on the adjacent surfaces here and here within the skin depth of the surface producing equal and opposite currents. There's no further buildup of circulating currents in these windings, and the MMF diagram just goes up and down like this. In fact, in these surfaces between these layers, there's no flux and there's no MMF, and we have relatively low leakage flux here and here, it only goes up to I and never builds up to 3I. So you can see that there's much less eddy currents in the windings, and there'll be much lower proximity losses. So interleaving is a good thing. Now there are practical reasons why sometimes we can't interleave. But this gives us a tool then to work out what the effect of that is, and perhaps do partial interleaving or something similar. And we can discuss that using these MMF diagrams and analyze the effects. So here's a partially interleaved transformer where we have 4 layers of secondary and 3 layers of primary, and there's a turns ratio. So really this is a transformer that is 3 to 4. And so here suppose we put 2 layers of secondary, then in the middle we have our 3 layers of primary, then we have the last 2 layers of the secondary. So we can draw our MMF diagrams. In this space here, we'll go to minus 3/4 I MMF. In the next space here, the total current to the left is what, minus 1.5 I, right there. With the primary, we've got plus 1 I, so this MMF is what, minus 1.5 and then plus 1. So here we're at minus 1/2 I. In this space, we'll add another 1 I, so we'll be at plus 1/2 I. And here we add another one, so we're at plus 1.5 I. Then we go back down by 3/4, so here we're at 3/4 I, and then we're back down to 0. So when we have diagrams like this, we will work out then what are the currents on each surface as a function of these MMFs in the air gaps, and then work out the proximity effect. Why would you want to do something like this and partially interleave? Well, in a lot of transformers, we're required to have insulation between the layers. The simple enamel insulation on magnet wire is good for about 70 volts, and then it breaks down. If we have higher voltages, and often where there are safety related things like insulating users from the power line, we'll have requirements of 5,000 volts or similar things, and so we may put tape between the primary and the secondary to achieve this insulation. And it's hard to fully interleave, or it's expensive labor to do that. So perhaps in this example we only need tape here and here, and this is something perhaps that's more practical and economical to build. So we've seen how to draw MMF diagrams both in simple cases and in more complicated interleave cases. We will use these MMF diagrams to analyze and calculate the proximity effects in complicated or arbitrary winding geometries. In the previous several lectures about the proximity effect, I've been using the terms turns of wire and foil or layers almost interchangeably. This is something that's actually done in the literature, and I want to explain it now in this brief lecture. In the last lecture, I used this example of a transformer with primary and secondary windings in which the flux lines are vertical through the window or air gap running between the turns. We didn't have flux running horizontally because of the symmetry of the winding. The winding actually made magnetomotive force that drove the flux vertically. So then we could think about a layer of wire, such as this first layer of 4 turns, inducing flux that goes in this uniform vertical direction. And indeed, later in that lecture, I approximated the round wire turns as uniform layers. In the next lecture, I'm going to discuss the one-dimensional solution of Maxwell's equations for this case. To do this, we need to approximate the turns of wire with a simple geometry, and what we will use is a uniform layer that spans the entire width or height of the window in the core. So we'll call, if this is our core here and here, we'll talk about a window width and have layers that stretch all the way from the top to the bottom that have a nice simple geometry that we can then solve analytically. The literature contains an approximation that is used in many of the papers in which a layer of round turns of wire are massaged and stretched into a uniform layer that looks like, say, copper foil. These are based on heuristic arguments. We can view them as an approximation, but the approximation seems to work pretty well, and it's adopted in many papers by many authors. Here's a summary of what's done. Let's say we have a layer of turns of round wire where the wire has diameter d, and what we want to do is basically smush them or push them into an equivalent nice rectangular regular conductor of wire. We would like our equations to maintain the same wire resistance to correctly model the copper loss. If we start with wire of diameter d, the first thing to do is to square the circle into a square having a length h on a side, and we want to choose h so that the area of this square wire is the same as the area of the original round wire. Let's see, the area of the round wire would be pi r squared, or pi times d over 2 squared. And that should be equal to the area of the square wire, which is h squared. So we can solve for h. Take the square root of both sides and we'll get h equals square root of pi over 4 times d. So here's how we define h. The next thing we do is we push these square conductors together to get rid of the gaps between the squares, and what we'll get next, C then, is a single conductor having thickness h, but it's shorter because we've eliminated these spaces between the conductors. The final thing we want to do is stretch this conductor so that it fills the entire width of the winding, or width of the window in the core, which is this length LW. This distance here is the distance h times the number of turns. I'll just call that in. So we have to stretch this length h in to LW, the width of the window. Yet when we stretch, this area now becomes bigger than this area. The problem with that is that we would predict that the resistance of the conductor is lower than it actually is. So we have to compensate for that. Here's what's done in the literature for that. We define what's called porosity. It's as if the stretched conductor is full of little holes, like a sponge, that effectively reduce its area back down to the original area. The porosity then is defined as the ratio of the cross-sectional areas. It's the ratio of the original area divided by this new area. If you plug in our expression for h, you get this for the porosity. What we do then is we change the effective resistivity of the copper to reduce it by the porosity so that the resistance of the conductor comes out correct. With an actual winding and with real turns of round wire, you can plug into these expressions. And for round wire, a typical value of this porosity is 0.8, so that 80% of the area is actually filled with copper conductor in the original winding. If we have a foil winding that is the entire height of the window, then we could get a porosity of 1. Now, reduced porosity means that effectively the resistivity is lower. The resistivity affects the skin depth, and so we get an effective skin depth as well. We can plug into the expression for skin depth and find that there's an effective skin depth then, delta prime, that is the original skin depth divided by the square root of the porosity. So the porosity affects the skin depth. In the upcoming lectures, we're going to define this quantity phi, which is the ratio of the conductor thickness to the skin depth. Conductors with large values of phi are greatly affected by the skin effect and the proximity effect, whereas conductors where phi is much less than 1 will have very little impact from the skin effect. If we have a layer of round conductors, we can talk about an effective phi, which is h divided by the effective skin depth, and so this effective phi turns out to be this expression. So we have a simple approximation in which a layer of round wire is approximated by a foil winding of uniform geometry. In the next lecture, we will use this uniform geometry to write the equations or the solution of Maxwell's equations in the general case. In the previous lectures, I've discussed the proximity effect for what really is the limiting case of very thick conductors. We could also call this the high frequency limit. This is the case where the conductor thickness is much greater than the skin depth. We can view this then as a limiting case where the current distribution is these decaying exponentials inside the conductor, and essentially no current flows in the center of the conductor. We saw when we had multiple layers, these conductors made circulating currents in which the magnetomotive force would build up. So we could have current going one direction up one side of the conductor, the opposite direction down the other side, so that there are circulating eddy currents inside the conductors, and that this causes the MMFs to build up as we get more layers, and we get significant proximity effect. Of course, we have the opposite extreme as well of a very thin conductor, which we could also consider as the DC limit, where the conductor thickness is much less than a skin depth. And in this case, the current in the conductor is uniform. Simply all flows in one direction, and we have essentially a constant current density. In this case, we don't have proximity losses. And the resistance of the wire tends towards the DC limit. Now, there are problems with both of these limiting cases. Of course, in the high frequency limit, or for very thick conductors, we get significant proximity effect that can significantly increase the copper loss. In the DC limit, or for a thin conductor, the problem there is that when we make our conductor thin, we have high DC resistance. How do we build a conductor that has low resistance, large thickness, and can carry a high current at the same time? Well, naturally it turns out that the optimum is in between these limits. That between the low frequency and high frequency limits, there's an optimum. In other words, there's an optimum thickness that minimizes the total loss. To find that optimum, we need to solve Maxwell's equations for the real current distributions in the conductor when the conductor has a moderate thickness that is in the vicinity of a skin depth. In this lecture, I'll describe that solution. There's a classic solution in the literature called Dowell's equation, which is a one-dimensional solution of Maxwell's equations. It's assuming the flux takes these straight lines alongside a simple layer that has this simple rectangular geometry, as we've discussed in the previous lecture. And through this solution of Maxwell's equations, we can work out the equation of the actual copper loss as a function of any conductor thickness. So what we will do is assume that we've drawn the MMF diagram of the winding, and we know what the H field is, or the MMF, on the two sides of a layer. We're going to assume that the waveforms are sinusoidal so that we can do a phasor or AC sinusoidal analysis of the linear system, and we can solve Maxwell's equations. I'm not going to go through the whole solution, but I am going to summarize the results and talk about how to use the results, and we will use these results then to design good transformers and inductor windings. Here is the solution. The equations on this page are called Dowell's equation. The first equation here is the copper loss in one layer. It's a function of the DC resistance of that layer. Phi, we talked about in the last lecture, it's the ratio of the conductor thickness to the skin depth. And we have this transcendental equation with G1 of phi and G2 of phi that are given by these hyperbolic sines and cosines as shown here. It's also a function of the magnetomotive forces on the two sides of the layer. It's not obvious looking at the transcendental functions of how they behave. This is something that probably is not design oriented. However, it is something that is in closed form. You can type these equations into a spreadsheet like Excel or into a calculator or into MATLAB and easily evaluate them. When we draw the MMF diagram of a winding, the change in the MMF from one side to the other of a layer is determined by the number of the amps in the layer, right? The change in the MMF from applying Ampere's law will be equal to the turns or the amp turns of that layer. So we can relate the MMFs to the current in the layer. Further, we're going to define a quantity lowercase m and define lowercase m with this equation where the MMF on one side of the layer is proportional to the amp turns of the layer with constant of proportionality equal to m. In fact, when we drew the MMF diagram in previous lectures, we get something that would look like this, for example, and the MMF would build up. So we can also almost think of m as being the layer number in such a case. So here, if this is Ni, this is 2Ni, 3Ni, the lowercase m is 1, 2, or 3, and it's the layer number in this particular winding. Combining these two equations, the change in MMF from one side of the winding to the other, we can write as m minus 1 over m by simply solving these equations. And so we can eliminate the MMFs in Dowell's equation in terms of the amp turns or current in the layer and the quantity m for that layer. If you take this and substitute this into those equations on the previous slide, here's what we get. And this is a very common way to express Dowell's equation. So here P is the copper loss of the layer. This Q prime has the transcendental functions from the previous slide. It's written then in terms of the layer number m. Here's a plot of that. So this is the vertical axis here is what we sometimes call F sub r. It's the ratio of the actual copper loss to the copper loss that would be caused by the DC resistance of the winding. So this is the factor by which the proximity effect increases the copper loss. This is on a log scale, as you can see. 1 is what we would like to have, so we have a resistance equal to the DC resistance. But here we're getting 10 and 100. We're getting big numbers from the proximity effect. Phi here was the conductor thickness. It's the ratio of the conductor thickness H to the skin depth. So this is really the thickness of the conductor. And then lowercase m is the layer number. What we can see is that for thin conductors with low phi, we go to the DC resistance. For very thick conductors, then the proximity effect becomes important, and especially when we're in a conductor that is in a high number of layers or high MMF environment, then we can get orders of magnitude increase in the copper loss. This plot suggests that what we should do is use very thin conductors and be down here. That's not quite the right answer, because if you use thin conductors, then the DC resistance is high. So we're starting out with thin wire that has high DC resistance to begin with. What we want to think about here is not the factor by which the loss increases, but just the absolute number. How big is the loss? It turns out that there's an optimum conductor thickness that minimizes the total copper loss. This is a similar plot, except that the denominator is a constant. What's been done here is the numerator, P, is the total copper loss in the layer, but the denominator is the DC loss that we would get in a conductor having a thickness of 1 skin depth. So it's I squared times RDC, where RDC is for a conductor having phi equal to 1, or 1 skin depth. That denominator simply normalizes everything. So what we can see here is that as we go to very thin conductors, the DC resistance becomes large. As we go to very thick conductors, we head towards the high frequency limit, which is what we calculated in earlier lectures that were for very thick conductors. And if you look at the plots, for a given value of m, there's a minimum. So for example, with m equals 3, there's a minimum right there. For layer 3, the optimum conductor thickness is this value, which is what, 0.7 skin depths. And that will minimize the total loss. The minimum values depend on the layer number, but they're more or less in the vicinity of phi equals 1. The plot on this slide and on the previous slide are the solutions of Dowell's equation for the general case of arbitrary conductor thickness. This is the equation that we use in practice to optimize a transformer or inductor winding. In upcoming lectures, we'll do some examples with this. Now let's consider working out the proximity loss in a transformer winding. Let's suppose we have a 2-winding transformer that has a total of capital M primary layers and capital M secondary layers. So the MMF diagram then will look like this, where we'll build up the MMF with a first layer of little m equals 1, second layer little m equals 2, and so on up to the innermost layer having little m equals capital M. And then we have secondary layers. If we assume we have the same wire for this simple example and the same number of layers, then our MMF will build back down from capital M down to 0. So for each layer, we can evaluate Dowell's equation with the appropriate value of little m. To find the total proximity loss, we need to sum Dowell's equation from little m equals 1 up to little m equals capital M. So then this would be the expression for the total loss in the full winding. It's possible to sum that series, and here in fact is the closed form solution for this factor f sub r, that is the ratio of the actual copper loss with the proximity loss to the copper loss in the DC limit. So it's a function of capital M instead of little m. Here's a plot of this. It looks similar to the plot for a given layer but it's actually not. If you compare the plots numerically, they differ, this one and the one from the previous lecture. So again, we have the conductor thickness on the horizontal axis, h over the skin depth. We have this factor F sub r, that is the factor by which the proximity effect increases the copper loss, plotted on a log scale. And then here, these different curves are for different total numbers of layers in the winding, or the capital M quantity. Again, for thick conductors much greater than a skin depth, we get very large factors by which the proximity loss increases the total loss. As in the case of the single layer, we can also plot the loss relative to a fixed quantity. This plot is the total copper loss relative to the loss we get with a conductor thickness equal to 1 skin depth at DC. So the bottom is simply a normalizing constant, and this is a plot of the total loss in the full winding, say the full primary winding, as a function of conductor thickness. As in the case of the single layer, these curves have a minimum. For thin conductors, we get large loss. For thick conductors, we go to the high frequency limit, or the thick conductor limit, and in between there is a value of phi that optimizes the loss. So for example, with capital M equals 4, we have a minimum right about here, which is at phi is 0.7. There's in fact a different value of phi that optimizes the loss in each layer, but usually we're not willing to change our conductor thickness for each layer. Instead, we wind the winding with one size wire, and so then this gives us the size of that wire that minimizes the total winding loss. While this function looks fairly complicated, it is a transcendental function in G1 and G2 of phi. It is one that we can easily type into a calculator or a spreadsheet or MATLAB and evaluate. In an earlier lecture, we saw that interleaving the windings can significantly reduce the MMF between the windings and reduce the proximity loss. Let's, in this lecture, do some examples to work out the proximity loss as predicted by Dowell's equation for various interleaving cases. The first case shown here is a 6-layer transformer that is fully interleaved, meaning that the primary and secondary layers alternate. In this case, we had drawn the MMF diagram earlier. You would go from 0 up to I, where I is the total current in a layer, and then back down to 0. So we would have 0 MMF in these places, and simply I in a few places, and nothing more. In this case, each layer operates with F equals 0 on one side and an MMF of I on the other, which is the same as what happens in the first layer with little m equals 1. So every layer is effectively an m equals 1 layer, and in fact for the whole transformer, then the proximity loss will follow the total curve of capital M equals 1. In fact, they're the same thing in this case. Here is the plot from the last lecture of the total proximity loss or total winding loss for different values of capital M. So capital M equals 1 is this curve. And in fact, it's pretty much equal to the same value, just simply 1, for large values of conductor thickness. It actually has a minimum right about there that's slightly less, and then with conductor thicknesses less than a skin depth, we get increasing loss. So in the fully interleaved case, you can actually choose thick conductors and it will work pretty well. Or if you choose this optimum value right here, you can get a slight improvement. That optimum happens at phi equals pi over 2, slightly greater than 1. although again it's nearly constant for any phi greater than 1. So full interleaving is very good. When we discussed this in an earlier lecture, I noted that fully interleaved windings sometimes can be expensive to build and require a lot of labor, so sometimes we do partial interleaving. And we looked at this example where we have a transformer with 3 primary layers and 4 secondary layers, and we have insulation between the layers here and here where there's an interface between the primary and secondary. So in this case we need to work out the value of little m for every layer and then evaluate Dell's equation for each layer and manually sum the results to get the total proximity loss of the transformer. In this example, the primary layers carry current I, and there are 3 of those, so we have a total of 3 I amp turns out of the primary. The secondary has 4 layers. To satisfy the transformer equation, the amp turns of the secondary need to cancel the amp turns of the primary, so each layer of the secondary will have 3I divided by 4 layers is 3/4 I, and these currents flow in the opposite direction, so I'm going to call them minus 3/4 I. With this, we can draw the MMF diagram as usual. At each point, you simply count the amount of current to the left of the point. We have 0 here. We'll be at minus 3/4 I here. At this point, we have 2 of these, so we'll be at minus 1.5 I. Here we add plus 1, so we'll be at minus 1/2 I there. We add another 1, so we're at plus 1/2 I here. We add another 1, so we're at plus 1.5 I. This point is down 3/4, so it's 3/4 I, and then we finally go to 0. For each layer, now we need to evaluate its value of little m, what we were calling the layer number in the non-interleaved transformer. The value of little m for Dell's equation is found from the equations in the Dell lecture, and here's a general expression for little m. If we know the MMF on the 2 sides of the winding or of the layer, then we can evaluate here to find what m is. So for this secondary layer, f of h is this MMF, which is minus 3/4 I. The denominator will be minus 3/4 I minus f of 0 here, which is 0, and so we get minus 3/4 over minus 3/4 is 1. So m equals 1 for this layer. For the next layer, we've got minus 1.5 on the right-hand side, and we've got minus 3/4 on the left-hand side. We'll get minus 1.5 over minus 3/4, which is 2. So we have m equals 2 there. And so on. We can keep going in the same way to work out what little m is in each case. An interesting thing here that happens is that little m doesn't have to be an integer. In the non-interleaved case, m has the interpretation of being the layer number. When we have interleaving, we can get effective m's that are other values, including fractional values, such as these primary windings. And in fact, little m can be anything. M is in fact a measure of the environment, the AC field environment in which a winding resides. Smaller m is better than bigger m. Another thing I should note here is that which side of the layer is which is actually interchangeable. I could interchange f of h with f of 0 in this equation for m and get a valid result. And in fact, when you do that, you get a different answer. So for example, for this second layer, we calculated 2. Suppose I swapped the choice of side of which is f of 0 and which is f of h. So we could have f of 0 being minus 3/4 I over minus 3/4 I minus the other side, which is minus 1/2. When we do this, let's see, the denominator will be plus 3/4, so we'll get minus 3/4 I over plus 3/4 I, which is minus 1. So depending on which side you call h and which side you call 0, we could get two different answers, either plus 2 or minus 1. Which one is right? Well, in fact, they're both right. And if you plug m as minus 1 into Dowell's equation, it turns out you get exactly the same answer as if you plug little m as 2. So, in fact, for each layer, there are two possible values of little m, but when you plug them into Dowell's equation, you get the same answer. This slide gives some more examples of calculating little m for different secondary and primary layers. You'll need to calculate little m in the homework, and if you need more examples, there's some here. So now for each layer, we look on our plot from earlier lectures of the solution of Dowell's equation, and for each layer we look up its value of little m, its value of phi, to find the factor by which the proximity effect increases the loss for that layer. And we can sum them up for each layer in our transformer to get the total proximity loss and see the factor by which proximity loss increases the total loss of our partially interleaved winding. So interleaving the windings can be a big help. We can reduce the value of little m for various windings, and then that reduces the total loss of the transformer. I have to say, you have to be a little careful here. These equations assume that the currents in the windings are all in phase. And when they're in phase, then interleaving will tend to cancel out the MMFs, or at least partially cancel the MMFs, and reduce the proximity loss. But there are some kinds of magnetic devices, such as flyback transformers or sepic transformers, where the winding currents are not in phase. The Dowell's equations that I've presented here don't account for that fact. The literature does contain more generalized versions of Dowell's equations that account for winding currents that are out of phase. And the classic reference is this Vandelack and Ziogas paper that is referenced here, and it does include the full equations with the phase shifts between the currents. In the case of flyback transformers and sepic transformers, it turns out that interleaving doesn't help proximity loss much. So flyback transformers tend to have very large proximity loss, and interleaving doesn't really help. It's too bad. For those cases, really all we can do is reduce the conductor size to reduce the loss. We've seen that the curves have minima somewhere in the vicinity of phi equals 1. So with sinusoidal winding currents, there is an optimum conductor thickness near phi equals 1 that minimizes the total loss. If you have winding currents that include harmonics, it may be that the optimum thickness is some other value. We'll talk about that in an upcoming lecture. Minimizing the number of layers is a good idea. If we can make windings that are long and not very tall, so there are very few layers, then that will really help with the proximity effect. Another way to reduce proximity loss is through the use of Litz wire. Litz wire employs many strands of very thin wire that are wound together in such a way to produce effectively a large conductor. Here's an example. of Litz wire. This is served Litz wire. It has a plastic sheath on the outside, and on the inside there are many strands of very thin wire. If you take strands of thin wire and simply tie them together, what will make the current flow on all strands? It turns out that the current will still want to just flow on the outside strands and not on the inner strands. With Litz wire, the wire is twisted in such a way that each strand spins, on the average, the same distance on the inside of the bundle as any other strand, and likewise the same amount of time on the outside of the bundle, so that each strand presents the same impedance to the currents, and the currents tend to distribute uniformly between the strands. This is a way to eliminate any currents in the winding, and then it can greatly reduce the proximity effect. To use Litz wire effectively, we should make the strand diameter be significantly less than a skin depth, and when correctly sized, Litz wire can really reduce the proximity and skin effects. You do have to account, though, for the fact that Litz wire itself acts like multiple layers. So while the strands are very thin, the number of layers is increased, and your winding effectively has yet more layers in it. But Litz wire can work and be a good solution. Litz wire does have increased cost, and there's more insulation in the window area of the core, so you tend to get less copper in the window, so the DC resistance is increased. Also, there's some labor associated with making connections to all these strands. Generally with Litz wire, the enamel insulation on the strands has a low melting point so that you can dip the strands in a pot of hot solder to remove the insulation and make the connection to the wire. With regular copper magnet wire, we don't do that, and our insulation lasts at much higher temperatures. So with the MMF diagram plus Dowell's equation, we can work out the proximity loss in more complicated winding geometries and look at the effects of interleaving. The previous lectures treat the proximity loss when the current waveform is sinusoidal. In switching converters, often our winding currents are non-sinusoidal and may be switched or have switching ripple and so on. In such cases, we can use Fourier analysis to work out the effects of harmonics in the waveform. Maxwell's equations are linear, and so superposition applies, and it's valid to apply Fourier analysis, where we calculate the harmonic content of our waveform and then apply the proximity analysis with Dowell's equation to each harmonic of the waveform. So for example, let's suppose we have, say, a transformer winding that has a pulsating current such as this. This is a waveform we might have in the primary or secondary winding, say, of a forward converter. With a pulsating waveform like this, we can use Fourier analysis to find the Fourier series of the current waveform, and we can write it in some function like this with a DC component and with a Fourier series. Here J is not the square root of -1, J is the harmonic number. With Fourier analysis, we can actually work out that for this pulsating waveform, the Fourier coefficients, which are the RMS values of the current, are given by this expression. And their magnitude depends on the peak value of the current, I peak, and on the duty cycle. The DC component is D times I peak, which is the average value as usual. To calculate the copper loss in the winding that has this pulsating current, we calculate the loss at each frequency. So the DC copper loss is the DC current squared times the DC resistance. For each harmonic, the AC copper loss is given by a function that looks like this, and this is in fact Dowell's equation, assuming there's no interleaving, and assuming we have capital M layers in our winding. One little thing to note here, the value of phi changes for each harmonic. Phi, recall, is the conductor thickness divided by the skin depth, and the skin depth is a function of frequency that goes like 1 over the square root of frequency. So for harmonic J, phi J will be h over delta J, where delta J is the skin depth for harmonic J. Since this goes like, again, like square root of frequency, we can write that phi J is the square root of J times phi 1, where phi 1 is the value of phi for the fundamental component. So as we go to higher and higher frequency or higher harmonic number, our value of phi gets larger and larger, but it's a weak function of J, the square root function. So we can write Dowell's equation for each harmonic, and then we need to sum the Fourier series. So plug these into the sum for the Fourier series to calculate I squared R and add them up. Summing the series sounds like a pretty complicated thing. What I usually do is write a computer program, maybe a MATLAB program, to sum them up, and I'll go up to some high harmonic number and then just stop, terminate at some point. It's interesting to define a harmonic loss factor, which tells us how the harmonics increase the proximity and total copper loss. Here I define a harmonic loss factor is the total copper loss of the fundamental and harmonics divided by the copper loss of just the fundamental component. And so with that definition then, we can write that the total copper loss is the copper loss from the DC component plus this copper loss from the fundamental and all of the harmonics, where I1 squared RDC is the RMS fundamental component times the DC resistance. We multiply that by FR at the fundamental to get the proximity loss included in the fundamental component. And then we multiply by FH, which tells us the effect of all the harmonics on the total copper loss. The value of FH, of course, depends on the Fourier series of the original current. Just to see what happens, for the waveform of this forward converter, here's what FH looks like at D of a half. So FH, again, is the factor by which the harmonics increase the total copper loss. At low frequency, these curves tend to a number that's bigger than 1, and that's because the RMS value of the fundamental is smaller than the RMS value of the full pulsating waveform. So the total harmonic distortion of the waveform will increase the DC loss. At high frequency, we go to a larger number that also is fixed, and this is the high frequency limit with a very large conductor. The interesting thing here is that at intermediate frequencies, FH becomes large. What's happening here is that at these intermediate frequencies or intermediate values of phi, conductor size, the effect of the harmonics is large. The fundamental component makes a relatively low copper loss, whereas the harmonics make a large increase in total copper loss. So the harmonics have the biggest effect for values of phi1 a little less than 1. From our previous lectures, phi1 a little less than 1 was where we wanted to design the winding. So that choice is fine when we have a sinusoidal current, but when we have significant harmonics, it might not be the best choice. Here's the same plot for duty cycle of 0.3. The curves look smaller, but actually the scale is increased. The last scale maxed out at 10, this one maxes out at 100, and actually with lower duty cycle the effect of the harmonics is getting worse, and at D of 0.1 it's even worse yet with curves approaching 100. So the harmonics can have a significant effect depending on how you've designed your winding, and the moral of that story is that when we have significant harmonics we need to include them and sum the Fourier series. So harmonics can significantly affect the answer, and they can affect the conclusion on the optimum wire size, and they can affect it in both directions. If you have a significant DC component, the optimum solution might be to use a thicker conductor to reduce the copper loss of the DC component. On the other hand, if you have significant high frequency components, such as in harmonics, it may be that the optimum is a smaller conductor. Here we get into writing some computer programs to evaluate this in our quest to find the optimum. We've discussed basic magnetics, and we've also modeled the different types of losses in magnetic elements, including AC core loss, DC copper loss, and AC copper loss. Next, we're going to talk about how to design inductors and transformers. We'll discuss some of the classic processes used to design inductors and transformers, which are based on certain assumptions about which losses are dominant and what the key constraints are. Really, we should think of these as first pass designs that still need to be further optimized after all the losses have been modeled. Really, there are many different types of magnetic devices that operate with different constraints. So I'm going to talk about a few of those right now. And their constraints arise from which losses usually are dominant, and also on things such as whether they have an air gap or not, whether the flux density is chosen to simply avoid saturation, or whether it's something to be chosen to optimize loss. A first example is a filter inductor that has small ripple, such as the filter inductor in the buck converter that we talked about at the very beginning of this specialization. So for example, in a continuous conduction mode buck converter, the inductor is there to simply filter the switching harmonics. And we've talked about inductors running in continuous conduction mode that have small inductor current ripples such as this. So the current waveform is dominated by its DC component, and it has small ripple delta I. On the BH loop of the inductor core material, we know from Ampere's law that H is proportional to the winding current with some formula like this. If the current has small ripple, then H has small ripple as well. There'll be an average value of H that is proportional to the DC component of the current, and then there'll be some ripple superimposed that is proportional to the current ripple delta I. And on the BH loop, we go around what's called a minor loop, a small BH loop whose area is proportional to the ripple. In such a case, we expect the core loss to be small because it's proportional to the area of the BH loop, which also is small. On the other hand, we've already discussed filter inductors and why we add air gaps to them. We'll generally use an air gap so that the inductor does not saturate at its maximum current. So to design a filter inductor, we'll have a structure such as this with a core, a winding, and an air gap. It will have a magnetic circuit model such as this. We expect the core loss to be small. Also, since the inductor current ripple is small, we don't expect to have much proximity loss just because the AC component of current is small. And so we expect the loss to be dominated by what's left, which is just the DC copper loss, the DC component of current put through the DC resistance of the wire. The other constraint in this case is that we don't want the inductor to saturate at its peak current, so we choose the air gap and the operating flux density to be less than the value that saturates the inductor with some suitable margin. Another design choice is the selection of the core material. We could use a lower frequency core material in this case if the core loss indeed is small, and a lower frequency core material may come with a higher saturation flux density, which would be an advantage in this case. Another type of inductor is an AC inductor, and here's an example of what we call a tank inductor, in which there's a resonant LC circuit whose voltage and current waveforms have large AC components. In fact, when the L is in series with the C, there is no DC component, and all of the current is AC. So we think of this kind of inductor, an AC inductor, as having large ripple, and in this case, no DC. If we sketch the BH loop for this case, again, H is proportional to current, so with large variations in current that go positive and negative, the BH loop will have large positive and negative variations in proportion. We have a large area of our BH loop, so there will be significant core loss. With a large AC magnitude of current, there will be significant skin and proximity loss as well, so we have to account for all of the AC losses in designing such an inductor. We'll still want to use an air gap to prevent saturation of the core, but we may need to reduce the flux density below saturation in order to reduce the core loss, and we'll have to do a lot of work to minimize the proximity loss. Generally, we'll want to use a high frequency material such as ferrite that can operate with large flux swings while maintaining sufficiently low core loss. A third type of magnetic device is a transformer. Here's a conventional transformer as we've discussed in the past, where here I've drawn it as an ideal transformer in parallel with a magnetizing inductance. In the transformer, the magnetizing current, I sub m, is proportional to H in the core. Here's the primary voltage waveform that's switched like we might find in some kind of switching converter. When the voltage is positive, the magnetizing current increases, which makes us go up the BH loop with increasing H. When the voltage is negative, the magnetizing current decreases, which makes us go down the BH loop. In this example, as I've drawn it, there's a large area of BH loop, and so we may have significant core loss, and we need to include that in our design as a constraint. On the other hand, we're not worried about saturation of the transformer, at least not by current. If you recall, current is not what saturates transformers. It's too many volt seconds. So current that goes in the primary, we hope, comes out the secondary and doesn't flow through the magnetizing inductance and therefore doesn't cause saturation. So in a conventional transformer, the core loss is significant. We have large AC currents flowing in the windings, so copper loss and AC copper or proximity loss are usually important. We won't employ an air gap. The air gap simply reduces the value of magnetizing inductance, but doesn't really add any benefit. Often we'll choose a reduced flux density to reduce the core loss, and the constraint in the transformer design then is reducing core loss rather than preventing saturation. And because core loss is significant, we may need to use a high frequency ferrite type material. Here's another device that looks at first like a transformer, but I would prefer to call it a coupled inductor. It's really two filter inductors that are wound on the same core. Here's an example with a 2 output forward converter. We're going to be talking about examples like this in more detail in upcoming weeks. This is a forward converter that has two outputs with two transformer secondaries and two inductors. There's a trick that you can actually wind the two inductors on the same core. You can design them to have DC with small ripple. In this case, this two-winding inductor needs an air gap to prevent saturation. If the ripples are small, then the BH loop is small. The BH loop H is proportional to the sum of the amp turns of the windings. And so we can design this a lot like an inductor with an air gap, but we have more than one winding, which we need to account for. Yet another example is a discontinuous mode flyback transformer. This is also a two-winding transformer, except it really works like an inductor, not a transformer. In discontinuous mode, the ripple is large, so we'll have primary current that ramps up to a large value and then turns off when the transistor turns off. Secondary current then flows out the diode, also with large ripple, and then we have the discontinuous interval at the end. The magnetizing current is the sum of the amp turns of these two primary and secondary windings. This is proportional to the H in the core, so our BH loop generally is something with a large area that starts at 0, goes up to a peak, and comes back down to 0 like this. With large ripple, the core loss is significant. With large current ripple in the windings, the AC copper losses are significant. There's also a significant DC component. We need to worry about the peak flux density to not saturate the core, so we need to use an air gap. But we need to control the core loss as well. We have to use a high frequency core material. Flyback transformer can be pretty challenging to design because all of the losses are significant and have to be controlled and modeled. So in the upcoming lectures now, we're going to talk about how to design these different kinds of magnetic devices. We're going to start with classic design procedures, which really are first pass designs that make a lot of simplifying assumptions. Once we have a first pass design, then we're in a pretty good place where we can model all of the losses and try to refine our design to optimize the element. In this unit, we're going to talk about how to design inductors. And the object here is to be able to write the basic design constraints and then design a real inductor and go in the lab and build it to make it work in our switching converter. In this lecture, I'm going to develop the basic design constraints to do that. So let's start with a simple inductor that is, say, the filter inductor in a buck converter that runs in continuous conduction mode, and it has small ripple. So the object here is to design an inductor that has a certain inductance, L, which we've decided on based on the ripple and the switching frequency of our converter. It needs to carry a certain worst case current we'll call I max, so it's some maximum current. And at that current, the core will operate at some maximum flux density that we'll call B max, which hopefully does not saturate the core of the inductor. We want our inductor to have a certain resistance, R. Really, this is to limit the loss and achieve a high efficiency. Or alternatively, our inductor should exhibit some worst case copper loss that's based on the DC resistance of the inductor and this RMS current that we will put through it. With small ripple, we expect that the core loss and the AC proximity loss in this inductor should be small, and today we're going to ignore those things and consider only the DC copper loss of the inductor. We talked previously about the basic structure of an inductor, and we will use that here. So we will assume we have some kind of core with an air gap, and there are some turns of wire on this core. The magnetic circuit model, as we've talked about before, is this. There's a reluctance of the core and a reluctance of the gap, which can each be expressed with the usual reluctance formulas like this. Generally, the core has very high permeability mu, and that makes its reluctance, the reluctance of the core, be small compared to the reluctance of the gap. And so for this design procedure, we're going to ignore the reluctance of the core, say it's a small value that tends to 0, and consider only the reluctance of the air gap. So then our equation becomes this, that the amp turns of the winding equals the core flux times the reluctance of the gap. Now, what are the constraints in designing our inductor? The first one is the flux density. We don't want to saturate the core. We'll assume the core saturates at some saturation flux density B sat, which is some value that depends on temperature and the core material, and generally is plotted on data sheets. We want to operate our inductor at some maximum flux density B max, which hopefully is less than B sat. And we'll choose some B max to design our core around. When the inductor current reaches a value I max, then we will design our core so that it operates at a flux density B equal to B max. And so we need to write the equation that relates these. So from our magnetic circuit, the equation on the previous slide, we had Ni was equal to the flux times the reluctance of the air gap. The flux is equal to B times the cross-sectional area of the core. So we can plug that in to get this. And if we plug in I as I max and B as B max into this equation, we get this. And finally, we can plug in the equation for the reluctance of the gap from the previous slide. The gap reluctance was the length of the gap divided by the permeability mu naught of the air in the gap, and the cross-sectional area of the gap, which we'll take to be the same as the core area. So if you plug that in for reluctance, the cross-sectional areas cancel, and what we get is that Ni max is B max times the gap length over mu naught. So we're going to call this equation 1, and it relates I max to B max, but it's also a function of the number of turns that we choose and the gap length, which are both design choices that we haven't selected yet. Second equation, we want to achieve a certain inductance. And we choose that inductance to get the current ripple that we want. So we previously solved this structure for the inductance, and what we got is the inductance is the turns squared over the reluctance. We're ignoring the reluctance of the core, so we'll plug in just the reluctance of the gap here, and we get this equation that relates the inductance to the area of the core, the turns squared, and the gap. So this will be our equation number 2. It's another equation that relates the variables. We don't yet know what core we've chosen, so we don't know what AC is. We don't know how many turns yet. We don't know the gap length. They're all design choices. A third constraint is the winding area. We have to fit the wire through what's called the window, or the hole in the middle of the core. So if we have N turns of wire, we will carefully wind our wire around the core like this. So on, winding the core, the wire around the core. We need all N turns of wire to fit through this window in the core, and that constrains how big the wire can be. And this limits the resistance of the winding. So we can write an equation about this to say that the wire has to fit in the core. We're going to call W sub A the window area. That's this area available to wind our wire. We're going to call the bare area of the wire A sub W. So this is the area cross-sectional area of the copper of one turn of wire. We want to fit N turns, so we have a total area of N times that area of wire is the area of the copper that we'll put in the window area of the core, and that total area has to fit inside the window area W sub A. Now there's some more issues with this. As I've sketched here, the round wire doesn't pack perfectly inside the window of the core. There's some little spaces between the turns that waste window area. And so what we can write is that there is what's called a fill factor, K sub U. It's also called the window utilization factor, which is a number less than 1 that accounts for how well the wire packs in the window. So K sub U is actually the ratio of the window area to the total area of wire, or total area of copper, that we place in our winding. And we can write then that N times the bare area of the wire must be less than the fill factor times the window area. And this is our third constraint. Now actually there's a lot of reasons why KU is a number significantly less than 1. First of all, as I mentioned, the round wire doesn't pack perfectly. So this will reduce KU by some factor like 0.7 to 0.55 depending on the winding technique and how well the round wire packs. Also, A sub W is called the bare area of the wire. It's the area of the copper in the wire. The wire also has insulation. So here's the copper, and there's some insulation around it. Insulation takes area also. So this depends on the type of insulation. If we just use magnet wire that has a thin layer of varnish on the outside, then the varnish may reduce KU by maybe 0.95, so 5%. On the other hand, if we have thicker insulation, we can get much greater reductions in KU from that. Also, we typically will wind the wire on a bobbin. So we'll have some bobbin where we wind the wire around this bobbin, and then we fit the core through the bobbin. So maybe there's some EI core or EE core. And so the bobbin is plastic that takes up some area also. And finally, we may have to put more insulation between windings. This is particularly true in high voltage windings where we have to add extra tape for electrical insulation. There's all kinds of reasons why the fill factor is less than 1. You don't know ahead of time what your fill factor is going to be, but I can give you some starting numbers. For a typical low voltage inductor that we might wind by hand in the lab, a typical value of the fill factor is 0.5. For a transformer that operates off the power line, we have to put extra insulation to protect the users from power line transients, and so there'll be more insulation, and that'll reduce the fill factor by maybe another factor of 0.5. If we have a high voltage transformer with multiple kV, then we need even more insulation and may have fill factors of 0.1 or even less. And finally, we can go the other direction. We can use square wire that packs better, or we can use foil windings with thin insulation between the layers of foil and get fill factors maybe up to 2/3. Okay, the fourth constraint is the winding resistance. So this is the DC resistance of the wire. If we have a wire that is some length, I'm going to call it L sub B, and it has a cross-sectional area that is the bare area, A sub W, and it's made of copper that has some resistivity rho, then the classic formula is that the resistance of this wire is the is rho times the length over the cross-sectional area. Now rho for copper, the classic number at room temperature is this, 1.724 times 10 to the minus 6th ohm centimeters. This is at room temperature. At 100 C, rho is about 2.3. It increases with temperature. Okay, the length of the wire we can express like this. If we have N turns of wire and we have a mean length per turn on our core, then the total length of the wire is N times the mean length per turn. So the mean length per turn is the average length or circumference of a turn of wire on this particular core. The mean length per turn is a function of the geometry of the core, and it's something that you can get on data sheets for the winding bobbins. So finally then we get to this expression for the resistance of the wire as a function of the rho, the turns, the mean length per turn, and the area of the wire, bare area. So this is our fourth constraint. Okay, we have four equations. First constraint related the maximum current to the flux density in the core. The second was the equation of the inductance. The third was the fill factor of the winding. And the fourth is the resistance of the winding. So we have four equations. Here are all the variables in those equations, and I've grouped them in three categories. The first category here, cross-sectional area of the core, the window area of the core, and the mean length per turn of the core, are all functions of the core geometry. If we haven't picked a core yet, then they're unknown. Once we picked a core, then we know the values of these. And they come together. You pick a core, and then all three of these numbers are determined. So really, the three of these quantities determine the core size. The next list are things that are specifications. We have to know the values of these and have decided them before we start designing our inductor. So these are givens and they're known. And then the last category are design variables that are unknown. The number of turns, the air gap length, and the wire area are all things that we have to choose in our design process. So these are unknowns. So we have four equations. Normally we think of, to solve four equations, we need to have just four unknowns. The way I've grouped it here, we have three unknowns here, and we have one more unknown, which is the core size. What I'm going to do is to take the four equations, eliminate these three unknowns, and then for the remaining core size quantities, I'm going to group them all on one side of the equation and treat them as one unknown. And we'll put all the specification quantities on the other side of the equation. And that equation then will tell us what our core size is. Once we've chosen that, then we can solve for the remaining three unknowns from these equations. Alright, so if we simply do algebra on these four equations to eliminate these three unknown quantities here, here's what we get. We're left with this equation where these factors that depend on core geometry I push to the left side of the equation, and the factors on the right side of the equation are the known quantities or the specifications. So what you do is you plug in the specifications onto the right-hand side of the equation, and then we need to pick a core that satisfies this inequality. The left-hand side of this equation needs to be larger than the right-hand side, and if so, then any core that satisfies that will work. The left-hand side is called the core geometrical constant. It's a collection of quantities that depends on the core size alone, and we have tables fact, Appendix A that we'll talk about soon is a list of the values of the core geometrical constant for standard core shapes. The core geometrical constant really is a measure of how big a given core is for a given magnetic application, really for a given filter inductor application. And on the right hand side you can see how the different specifications affect the core geometry or the core geometrical constant. For example, if you make B max bigger, it makes the core geometrical constant smaller, and you can use a smaller core. Of course, we can't push B max too large or our core will saturate. Likewise, the resistance is in the denominator. If you allow more winding resistance, you can use a physically smaller core. The fill factor also is in the denominator. The inductance and the maximum current are in the numerator, so if we make those larger, we need a bigger core to do the job. Okay, once we've chosen a core that satisfies this, then we can go back to our other equations, where now we know the values. We picked a core, we know what the values of the core dimensions are. We can go back to these four equations and solve for the remaining unknowns for the turns, the gap length, and the wire to complete our design. In the last lecture, we derived the equations for the KG method of designing a filter inductor. In this method, the DC winding resistance is one of the design specifications. So we're trying to design an inductor that has a given DC copper loss. The other losses are ignored in this design procedure. Now I want to list all of these equations in one convenient place and illustrate how to use them. Here is a list of all of the specifications. And I've listed here units for each of these quantities. In the equations of the last lecture, all units were MKS, which is a good way to do it. But for convenience, I've listed some of these quantities in centimeters rather than meters, which is a convenient thing to do because when we have ferrite cores whose dimensions are centimeters and not meters. So here the wire resistivity is specified in ohm centimeters. Again, this is 1.724 times 10 to the minus 6th ohm centimeters at room temperature. The other quantities we're going to specify in MKS units. And then the core dimensions off of the data sheet are expressed in centimeters or centimeters squared in the following equations. When we have centimeters, then we have to add appropriate figures to convert from meters to centimeters. So the first step is to determine the core size. We plug in the specified values for all of these quantities into this equation. And then this tells us the required K sub G, or the required core size. In this equation, I've added a figure of 10 to the 8th to convert from meters to centimeters, so that Kg is in centimeters to the 5th power. So what we have to do is select a core that's large enough, has a K sub G at least this large. Appendix B contains magnetics design tables with data for standard ferrite core sizes and shapes, and also for American wire gauge wire dimensions. I've included a PDF file on the course website with this appendix. So here it is. It has lists of different magnetic core shapes. Here's a ferrite pot core shape, which is a round core. It's hollow in the middle where a bobbin goes that contains the winding. There are two core halves. Here's a sketch of what they look like when you put them together. Typically, all of these different core shapes are numbered, and the numbers are key dimensions of the core in millimeters. In the pot core series, for example, a 2213 pot core has a diameter A of 22 millimeters and a height H of 13 millimeters. The table also lists in the second column the geometrical constant K sub G in centimeters to the fifth power for these cores. And there's other dimensions here as well, such as the cross-sectional area, the winding area, and so on. There are also EE cores, EC cores, which are like EE cores except they have a round center post, so they're easier to wind and have a smaller mean length per turn. ETD cores also have a round center post. PQ cores are perhaps halfway between a pot core and an EE core. They have core sets with round center posts and bobbins, and they're nice because they come with bobbins that plug into printed circuit boards with standard pin spacings. Finally, at the end of the appendix is an American wire gauge table. So there's the wire gauge number on the left side. The second column is the bare area. So this is the cross-sectional area of the copper, not including any insulation. There's the resistance in microohms per centimeter of wire. And finally, there's the diameter of the wire in centimeters. We look in the tables and select a core that has a large enough K sub G, and then we note its dimensions: the cross-sectional area, the window area, and the mean length per turn. Next, we calculate the gap length. Here's the equation from the last lecture for that. It has a factor of 10 to the fourth to convert AC in square centimeters into square meters. The resulting gap length is in meters in this formula, and you'll need to convert that. Gaps don't really come in centimeters or in meters. Usually they're in small fractions, like fractions of a millimeter. I should note here that this formula assumes that the flux goes straight across the air gap. So here's our core, and it assumes that the flux is going directly across the gap like this, so that the air gap has the same cross-sectional area as the core. This isn't what really happens, especially when you have larger gaps, is that we get what's called the fringing effect, where some of the flux curves and does this. And the result of that is that effectively we have a larger cross-sectional area in our gap than we have in the core. Therefore, to get the desired inductance, generally you have to use a larger gap than this formula predicts. There are some approximate formulas that are well known that are used to estimate the effect of fringing on the cross-sectional area of the air gap. One of those formulas is that the cross-sectional area is increased in each of its dimensions by the air gap length. So if this is the air gap, here's our core area, that the air gap is increased, or the air gap has an increased area, where if the core has a dimension A, then the air gap cross-sectional area is A plus the gap. And likewise for the other dimension. We have B, we'll have B plus the gap. This is just an approximation, but it works pretty well in practice. Core manufacturers sometimes will sell gapped cores, and rather than specifying the gap length, they will specify what's called A sub L. And A sub L is the inductance in millihenries that you get if you wind 1,000 turns of wire on a bobbin on this core. It's also equal to the inductance in nanohenries per turn. So when you specify A sub L, Then it's up to the core manufacturer to deal with fringing and any other effects there are, and they'll supply a gapped core that will give the proper inductance according to the A sub L formula. So here is how to calculate A sub L in terms of the inductance, and so alternately we could specify A sub L instead of a gap length. The next step is to determine the number of turns. Here's an expression for that from the last lecture. It has a factor of 10 to the fourth included again to convert square centimeters in A sub C into square meters. Knowing the turns, then we can calculate the wire gauge. The wire has to fit inside the window of the core. So we had this equation from last time that N times the wire area should be less than the fill factor times the window area. From this formula, knowing the turns and the window area and estimating the fill factor, we can calculate the required wire bare area. With that calculation, then we can go to the wire table in Appendix B to select a wire size. Here again is Appendix B. This is the wire area. It's the bare area, again the area of the copper cross section, and the units in this table are 10 to the minus 3 centimeters squared. So for example, 10 gauge wire has a cross-sectional area AW of 52.41 times 10 to the minus 3 square centimeters. So we need to select a wire gauge that will fit in the window. So we select the next smaller wire size that satisfies the design equation. Lastly, as a check, we can calculate the DC resistance of the winding and see if it meets our requirements. Here's our familiar formula for resistance of a length of wire. We have N turns of wire where each turn has a length MLT, the mean length per turn. We use the resistivity and the wire area, and we can calculate our resistance and see if this inductor will meet our requirements for the given resistance. Briefly, here's a little example then of what can happen. So here's a boost converter with an inductor. Let's suppose our boost converter operates in continuous conduction mode with small ripple. For this example, we have a fixed input voltage of 25 volts, and we have a fixed input power of 200 watts. So our DC current would be 200 watts over 25 volts, which is 8 amps. Now the inductor has ripple, so there's AC current as well. Let's suppose we've designed an inductor with a switching frequency of 100 kilohertz and an inductance of 30 microhenries. You can work out the ripple. In this case, it is deep into discontinuous mode and has small ripple, at least at low duty cycle. If we go through the design procedure, following the equations on the previous slides, we may select a PQ2620 core for this example. And when we go through the process, we calculate that we need 10 turns and we need 15 gauge wire. So we could go into the lab with these numbers and wind such an inductor. It's interesting to see what happens to the other losses in the inductor that we've ignored so far and how they vary as we change the duty cycle. Of course, as we change the duty cycle, the output voltage will go up. What we're going to do is maintain a fixed input voltage and fixed input power and vary the duty cycle and the output voltage. To calculate the other losses, we need to work out the equations for the core loss for this. We also need to work out the proximity losses, so we should figure out how many layers this winding will have. How many turns of 15 gauge wire will fit in one layer on this core? To figure that out, we need to go to the data sheet and look at the bobbin dimensions to see what the geometry of the winding will be. To do that, we can go online and download the data sheet for this core. Here it is. And if we scroll down, there is a drawing and dimensions of the bobbin. This bobbin has a winding width of 9 millimeters. and it has a height from the bottom of the bobbin to the top, 3.8 millimeters. Our wire, number 15 gauge from the wire table, has a diameter 1.53 millimeters. So when we lay wire, when we wind the wire, we're not going to get 10 turns in 9 millimeters. 10 turns would be 15.3 millimeters in width. So there'll be 2 layers. We can actually have 5 turns per layer and 2 layers to get the winding to fit. So we have a 2-layer winding, capital M equals 2. We can work out what phi is for this 15 gauge wire. 15 gauge is pretty thick. At 100 kilohertz, phi turns out to be 6.2. This is the wire diameter divided by the skin depth at 100 kilohertz. And our 15 gauge wire is 6 skin depths in thickness. So you would expect there to be proximity loss. However, if the ripple is small, then there won't be much AC current, and the total proximity loss may be small compared to the DC loss, just from the 8 amps of DC in the winding. We can calculate the ripple and plug that into the proximity loss equations from earlier lectures. And I won't go through that in too much detail, but just to say here's a result. We're varying duty cycle on this axis from 0 to 1/2. At D of 0, there's no switching and no ripple, whereas as we increase D, then we'll get more and more ripple, and that will cause more AC loss. Here is a plot of the ratio of delta I to the DC component, capital I. Capital I is a fixed 8 amps, and delta I is some fraction of that. As we vary D from 0 to 1/2, the ripple goes from 0 to about almost 40% of capital I. If you work out the losses, the DC copper loss is a fixed value because we have a fixed input current in this example, and it causes a loss of just under 0.4 watts in the DC winding resistance. When we calculate proximity loss, it will go up as the duty cycle increases because delta I is increasing. And the core loss also goes up, but it's significantly less than the proximity loss for this example. Here's the total loss then, which is the sum of all 3 loss components. And the assumption that we ignore the AC losses in this filter inductor example perhaps is a good assumption at low duty cycle where delta I is relatively small. But when we get delta I that's 40% of the DC component, for this example, the proximity loss starts to get big, and it's actually larger than the DC component of loss for duty cycles above about 0.44. The point of this example is to illustrate that the KG method is a good starting point to get a preliminary design, but it doesn't include a lot of the other loss components, and in fact, we really can't calculate the proximity loss until we know what wire gauge and how many layers we have. So we have to do a first pass design before we know those things. Having done the first pass design, now we're in a position where we can calculate the other losses and perhaps adjust or refine our design. For example, if this total loss at high duty cycle is too large, we could think about how to optimize the wire gauge to reduce the proximity loss. Next, let's consider how to design inductors that have multiple windings. We can actually generalize the KG design method to include transformers, inductors, and other elements that have more than one winding on the same core. The KG method is applicable whenever the DC copper loss dominates the total loss of the system and whenever we are designing to operate with a given maximum flux density. The key extension in the multiple winding case is to decide how to allocate the winding area between the various windings and therefore to allocate the different wire sizes for the various windings. So let's suppose we have multiple windings on a single core. We know what turns ratios we want between the windings. And let's suppose we have a core that has some total window area, WA. And of course we have the other quantities as usual, such as mean length per turn and fill factors. The question is, how do we allocate this total window area between each of the windings? We can think of it this way. Here's the window, and we may allocate some amount of this window to the first winding, and we'll put however many turns we need for that winding into that area, and that winding will have wire of some size that we need to decide. So what we'll do is, of the total window area W sub A, we'll allocate a fraction alpha to the first winding. Likewise, we can allocate some fraction alpha 2 to the second winding, and so on. Of course, the fractions, the alphas, are all numbers between 0 and 1, and they have to add up to 1. We could arbitrarily choose all the alphas, but of course there is an optimum choice for each alpha that causes the total copper loss of the inductor to be minimized. Let's write the equations of the copper losses in each winding. We can say the copper loss in winding number J is equal to its RMS current squared times the resistance of its winding, and the resistance of winding J is the resistivity rho times the length of that winding divided by the cross-sectional area of the wire. And the length of the winding is the number of turns of the winding multiplied by the mean length per turn. The wire area we can write as the window area available to that winding, which is the window area of the whole core multiplied by the alpha for that winding, and then multiplied by the fill factor. We need to fit in turns into that area, so if we divide by the number of turns, we get the wire area for winding J. And finally, we can plug all of these things in, and what we get then is the resistance of winding J is given by this function, and the copper loss is given by this. The important thing here is that the copper loss for winding J goes like 1 over alpha J. So of course the smaller alpha J is, and the less winding area we allocate to this winding, the more its copper loss will be. We can do this for each of the windings, and then the total copper loss is the sum of all these individual copper losses, and so we can add them up. Let's consider what happens to the total copper loss of the overall device as we change one of the alphas. So for example, suppose we change alpha 1, starting from 0 and going all the way up to 1. What happens? Well, at alpha 1 is 0, then winding 1 has infinite loss because its wire size is 0. On the other hand, the rest of the windings have more area, and so they have less copper loss. In the other extreme, as we let alpha 1 go to 1, then the copper loss in winding 1 is minimized, but the copper loss in all the other windings goes to infinity because those wires go to 0. So if we add all the copper losses together, there's some optimum value of alpha 1 that leads to a minimum total copper loss for the system. With k total windings, this is a k-dimensional optimization problem, but there are optimum values for each of the alphas that minimize the overall system. From calculus, this optimization problem can be solved using the method of Lagrange multipliers. What we want to do is minimize this function, this total power loss, and it's subject to the constraint that all the alphas add up to 1. So we want to find the optimum value of every alpha subject to this constraint. With the method of Lagrange multipliers, what we do is we define a function f of alpha that is equal to this quantity to be minimized, the total power loss, plus this Lagrange multiplier, C, that gives us the constraint. So this G of alpha is the constraint. G of alpha is 1 minus the sum of the alphas, so that this is a quantity that should add up to 0. And the method of Lagrange multipliers from calculus tells us that the optimum point is a solution of this system of equations where we take the partial derivative of f with respect to each of the variables, set those partial derivatives to 0, and solve. And without going through all of that algebra, I can give the answer. The answer is that the Lagrange multiplier Xi turns out to be this. And this quantity, in fact, is the optimum value of the total power loss. And then the alphas turn out to be this. So what this function says is the optimum alpha is equal to the amp turns of the respective winding divided by the sum of the amp turns of all of the windings, where here the amps are the RMS current specified for this winding. An alternate form is to replace the turns with the voltages on the windings, because the voltages are proportional to the turns. So you often see this answer expressed in this form, and it's an equivalent form, where alpha M is the product of the voltage on winding M multiplied by the RMS current of winding M divided by the sum of the volts and currents for all of the windings. Here is the key result, where we allocate the winding area according to the apparent powers of each winding, where the apparent power is the RMS current multiplied by either the peak voltage or the RMS voltage of the winding. Whether you use RMS or peak voltage doesn't matter as long as you apply that consistently. Let's do an example. Suppose we want to design the transformer of a full bridge converter using this method. Here is what the current waveforms look like in each of the three windings. In the primary winding, we have the secondary current reflected to the primary, and that's what flows during the D intervals, and we have 0 the rest of the time. In the secondaries, we have a center tapped secondary with a full wave diode rectifier circuit. During the D intervals, we have the entire inductor current flowing in one of the windings during the D interval. During the D prime interval, this inductor current splits, so half of it flows this way and half flows that way, and we get half the output current in each winding. So we get waveforms like this, and it's interesting that the wave shapes of the primary and secondary windings are different, and therefore they have RMS values that don't scale according to the turns ratios. We can work out expressions for the RMS currents in the windings. We square and integrate over a period, divide by the period and take the square root. Or you can look these up in Appendix A, the table of RMS values of commonly observed waveforms, and both of these occur there. For the primary, we get this expression that depends on square root of D. And for the secondaries, we get an expression like this that depends on the square root of 1 plus D. If we plug those expressions in then to the expression for the alpha, we get this result for the primary, alpha 1, and we get this result for alpha 2 and alpha 3. They are different expressions, and they have different dependencies on the duty cycle. In practice, of course, we're not going to change our wire gauge depending on what the duty cycle is. We have to choose one value. So we will design to optimize the transformer, perhaps at some worst case point, and evaluate these expressions at the duty cycle for that point. Here's an example then. Suppose we want to optimize the transformer design at duty cycle of 3/4. If we plug in D of 3/4 into the expressions on the last slide, we get that alpha 1 is about 40%. Alpha 2 and alpha 3 are about 30%. So we give 40% of the window to the primary and 60% of the window to each half of the secondary. The total copper loss then will turn out to be this. Since the secondaries have to conduct extra current during the D' interval, they incur extra copper loss, and the optimum solution then turns out to give more than half of the window area to the two secondary windings, and the primary only gets 40% instead of 50%. So to optimize a multiple winding magnetic device, we divide the window area according to the apparent powers of each winding. Having done that, then we can employ all of our previous design equations from the KG method to design the multiple winding magnetic device. Now let's consider how to design an inductor that has multiple windings on a single core. An example of a converter that could use coupled inductors is the SEPIC or the Chuk converter or some other converters that have more than one inductor in them. Also, the flyback transformer really is the inductor of a buck-boost converter with two windings on it for the primary and secondary. Flyback transformers can be designed this way as well. Finally, with multiple output converters, for example, multiple output forward or full bridge converters, we have an inductor in each output, and these inductors can be coupled and designed with this approach as well. Here's the transformer model of a multiple winding inductor, where the magnetizing inductance performs the function of the inductor that we're going to design. But we have multiple windings that are coupled through an ideal transformer in the model, and I've represented winding resistances for each winding as well. We're ignoring the leakage inductance in this design. Physically, we could build such a device with a simple core, as we have used for single winding inductors, where the core has an air gap and it has multiple windings. So we put our first winding, say, on it. We could then wind our second winding here, and so on. A magnetic circuit model for this structure would include the usual reluctances of the core and the gap, for the core here and the gap. And then Ampere's law tells us that the total MMF across the reluctances of the core and the gap is equal to the total amp turns that pass through the window in the core. And that total amp turns would be what is the magnetizing current in the circuit model, IM. So it's the sum of the amp turns of the windings, and here it's referred to the primary winding N1. Indeed, by simply solving the electrical equivalent circuit for I1, I2, and all of the winding currents up to IK, the magnetizing current is found by the node equation at this node, and it's equal to I1 plus the sum of the reflected currents of the other windings, like this. Now we need to write the equations for designing this inductor. They're similar to the single winding inductor design equations, except that we incorporate optimization of the winding area with multiple windings. The magnetizing current is what drives flux through the core. From solving the magnetic circuit model, we get that the MMF of the magnetizing current is equal to the flux phi times the reluctance of the core plus the gap. And we'll, as usual, assume that the reluctance of the gap dominates the series combination and simply write gap here. As usual, we want to design our inductor so that a maximum flux density occurs when we apply a specified maximum current. So we can plug in I max for the magnetizing current, and we can plug in B max for B, and what we get is this equation. It's similar to the equation for the single winding case, except that we have this total magnetizing current, which is the sum of the amp turns of the windings, referred to the primary. We want to obtain a specified magnetizing inductance, and as usual, the magnetizing inductance is given by the turns squared divided by the reluctance of the gap. So we have this equation as a second constraint. We want to achieve a certain total copper loss, which is the sum of the copper losses of all the windings. From the previous lecture, we found that the optimal design with the optimal allocation of the window areas among the windings led to this copper loss. So this equation is from the previous lecture. I tot here is in fact the magnetizing current, or the sum of the currents referred to the primary winding. With these equations, then we can again eliminate the unknowns and derive an equation for the kg of the core that is required. And the derivation is very similar to what we did for the single winding case. So here's what we get when we eliminate unknowns. We can get an equation for the total copper loss in terms of these quantities. We can put the known or specified quantities on the left-hand side. And on the right-hand side, we get the core geometry, which is in fact the kg of the core. And so what we have to do is select a core with a kg at least this large. Once we found that core, then we can look up its cross-sectional area, window area, and mean length per turn, and calculate the turns and the wire gauges and the air gap for the various windings. So we can extend the kg design method for the case where we have an inductor with multiple windings. Here in one place are the steps to perform a first pass design of a coupled inductor using the case of G method. Here are the quantities that we need to specify ahead of time. And what's new for this case is that we need to know this I tot quantity, which is the sum of the RMS currents in all the windings referred through the turns ratio to the primary winding. We also need to know the peak value of the magnetizing current. So this is the peak value of the instantaneous currents, all referred to the primary winding and added together. We need to know the desired turns ratio. We need to know this desired value of magnetizing inductance, which is the inductor of the filter inductor, and it's referred to winding 1. Then we'll specify, in this case, the total copper loss, PCU, and as usual, the winding fill factor and the maximum flux density. The steps are very similar to the single winding case. The first step is to determine the core size. We evaluate the right-hand side of this equation using the units given on the previous slide, and out of Appendix B we select a core having a case of G at least this large. Next we calculate the gap length using this expression. The result is expressed in meters, and as I mentioned previously, because of fringing, it may be necessary to use a slightly longer air gap to get the correct gap reluctance and inductance. Next we determine the number of turns. So for the primary turns, we use this expression, and then for the other windings, we choose their turns according to the desired turns ratios. The next step is to evaluate the alphas, or the fractions of the window area that are allocated to each winding. And as we found several lectures ago, the optimum value of the alphas is to divide these according to the apparent power or the ampere turns of each winding. So alpha 1 will be the fraction of window area allocated to winding 1, and so on. Next we evaluate the wire size. Once we know the alphas, then for example winding 1 can have a wire area that is alpha 1 times the window area times the fill factor and divided by the number of turns for the primary winding. We can then look in the wire gauge table at the end of Appendix B to select the actual wire gauges. So we have a simple first pass design procedure for multiple winding inductors such as flyback inductors, coupled inductors, and so on. As usual, it's important after doing the first pass procedure to work out other losses that have been ignored so far, such as core loss and proximity loss, and then possibly further refine the design. Let's consider the example of design of a coupled inductor for the output filter inductors of a 2-output forward converter. Here is the circuit. For this particular example, we're building a single isolated converter with a single transistor and control loop that produces 2 different output voltages to do 2 different loads. The first output is a 28 volt output, the second is a 12 volt output. We built 2 secondary output circuits for this forward converter to supply each of these 2 outputs. And we choose the turns ratios between the secondary windings of the transformer according to the desired ratio of output voltages. In this circuit, it turns out that the voltages across the windings of the 2 filter inductors have the same waveform and are proportional. In fact, they're proportional according to the ratios of the output voltages. For this reason, we can wind the 2 inductors on the same core and build a coupled inductor. It's valid to do that when the 2 windings have the same applied voltage naturally in the circuit, and when we choose a turns ratio that follows that voltage. This is often done in multiple output forward converters for 2 reasons. First, we have only 1 output magnetic assembly instead of 2 or more, and so it reduces the manufacturing cost. Second, it improves what's called the cross-regulation. In a circuit such as this, we have only 1 feedback loop to adjust the duty cycle of the single transistor, and so we can control or regulate the output voltage of one of the outputs. What we would like is to have the other outputs track, and the accuracy by which the output voltages track each other is called the cross-regulation. In this circuit, they do track each other pretty well as long as both outputs operate in continuous conduction mode and in steady state. However, if for some reason an output current becomes small so that this output circuit operates in the discontinuous conduction mode, then its voltage will tend to rise, and the cross-regulation between the outputs is not so good. When we couple the inductors, we observe that even in that case, the voltages tend to track each other very well because of the transformer action between these coupled inductors. So we'll design a coupled inductor in which the turns ratios of our coupled inductors is the same as the turns ratios of the secondary windings. For this example, we have a 28 volt 4 amp output for the first output, and the second output is a 12 volt 2 amp output. The DC components of the inductor currents then are 4 amps and 2 amps respectively. Here's an equivalent circuit of the coupled inductor inserted into the forward output circuits. We've neglected leakage inductances. There is a single coupled inductor that carries the DC components of the currents of both windings, of course reflected through their turns ratios. The voltage applied to the coupled inductor then is this switched waveform that is positive during the D interval and negative during the D prime interval. This voltage waveform causes the magnetizing current waveform to look like this, with its usual wave shape having a DC component plus some ripple delta IM. The magnetizing current then flowing here is the sum of the 2 currents. It would be I1 plus the reflected I2. Let's suppose we design this inductor to operate in continuous conduction mode at this quiescent operating point at D of 0.35. Suppose we decide we want a ripple delta IM to be 20% of the DC component of IM. And let's suppose that we're going to operate at 200 kilohertz. The DC component of the magnetizing current then will be I1, the 4 amps, plus the reflected value of I2, so 2 amps multiplied by the turns ratio of 12 over 28, gives us a total IM of 4.86 amps, which is the DC component. Our delta IM would then be 20% of that. We can calculate the ripple in the usual way. Delta IM is the applied volt seconds divided by the inductance with a factor of 1/2 to get peak to average ripple. This expression uses the D prime interval, where we have negative the output voltage applied during that interval, and we change by -2 delta IM. The volt seconds then are the V1 D prime TS, and divide by 2 LM to get delta IM. Solve for LM, we'll get this, and let's make delta IM be 20% of capital IM. We find that we need an LM of 47 microhenries, and the peak magnetizing current then would be the DC component plus the ripple, which works out to be 5.83 amps. We need to find this quantity I tot, which is the sum of the RMS currents referred to the primary. With small ripple, we can ignore the effect of the ripple on the RMS value and simply use the DC components for the RMS values, refer them through the turns ratio to get 4.86 amps. If you want to include the ripple, there are formulas in Appendix A for the RMS values that will slightly increase these figures. Next step is to evaluate K sub G. We need to specify a total copper loss. This is a design choice. One thing we can use to guide us is the thermal resistance of typical cores, and to allow a copper loss that does not lead to an excessive temperature rise. Here in Appendix B are data for pot cores. The next to last column is the thermal resistance of the core. This is an approximate number that assumes the core is simply sitting in air without additional fans or cooling. And we have thermal resistances in degrees C per watt of loss. We don't yet know which core we're going to choose, but for an application such as this, we may end up with a core such as the 2213 or 2616 cores that are a moderate size, and we have thermal resistances of 30 or 38 degrees C per watt. A typical choice might be 3/4 of a watt of total copper loss. With a 2616 core, that would lead to a temperature rise of 30 degrees C times 3/4 of a watt. So a little over 20 degrees C rise in our inductor, which is a very reasonable and conservative number. After choosing the core and completing the design, we may need to check what the temperature rise will be and possibly reiterate with a different amount of allowed copper loss. Other core geometries don't always have thermal resistances published, but you could expect that a similar size core with similar dimensions would have a similar thermal resistance. So let's allow 3/4 of a watt of total copper loss. Let's also choose a Bmax of 0.25 Tesla. This will keep us from saturating. Typical saturation flux densities for ferrite are between 0.3 and 0.5 Tesla, and they decrease as the temperature rises, so this will give us some margin. Let's also assume we'll have a fill factor, K sub U, of 0.4. This is a reasonable estimate for a low voltage winding where we have multiple windings and may have insulation between the windings. So with all of those design choices, we evaluate K sub G, and what we find is we need a K sub G of at least 16 times 10 to the minus third centimeters to the fifth power. We go to Appendix B to look at the ferrite core tables. I've decided for this design to use a PQ type core. We need a PQ core with a kg of at least 16 times 10 to the minus third. And the smallest core on the list, the PQ2016, is slightly larger than that, so that's the one we'll choose. Here is the window area, the cross-sectional area, and the mean length per turn for this core. Here then is the selected PQ core, the PQ2016. It has a long dimension of 20 millimeters, and the height of the core is 16 millimeters. Next, we calculate the air gap. When we evaluate the formula there, we find we need a total air gap of 0.52 millimeters. Note that when the flux goes around the core, it will go across two air gaps. So we would generally, if we add spacers, space the core halves apart, and the flux will cross two air gaps. So we need each air gap to be half of this length, or 0.26 millimeters each. Next, we evaluate the turns. Our formula for turns gives us 17.6 turns, and the second winding must be the desired turns ratio, 12 over 28 times that, which gives 7.54 turns. We really can't have fractional turns, so we have to round these off. We'll round them off to 17 and 7. This will give a slight inaccuracy in the ratio of output voltages, but we also have other things that affect the output voltage, such as the diode drops, so it may be necessary to slightly adjust the turns later. Now we choose the wire sizes. First we have to allocate the window area. Now that we know the number of turns, alpha 1 is 17 times the 4 amps for the first winding, divided by 17 times I tot, which was 4.86 amps, and this turns out to be 0.8235. So 82% of the window area goes to the first output, and the remaining 17% of the window area goes to the second output. Given those alphas, now we can calculate the wire gauges. For the first output, we find that we need a wire whose bare area is 4.96 times 10 to the minus third square centimeters. We look in Appendix B at the wire table, and we need to choose the largest wire whose area is no greater than that number, 4.9 times 10 to the minus 3. It looks like 20 gauge is a little too big. We need 21 gauge. Likewise, for the second output, we need a wire that's at least 2.48 times 10 to the minus third square centimeters, and 24 gauge is the largest wire that meets that criterion. So our first output will have 17 turns of 21 gauge, and our second output will have 7 turns of 24 gauge. Let's consider a second example, a continuous conduction mode flyback transformer. Here's the schematic from Chapter 6, including the equivalent circuit model of the transformer, consisting of a magnetizing inductance referred to the primary side and an ideal transformer. This is basically a two-winding coupled inductor. Here are the waveforms for the conventional flyback converter. We will design to have a certain magnetizing current and magnetizing inductance, and design for given current waveforms in the primary and secondary and their associated copper loss. We'll take these as the specifications of this converter. We have a 200 volt DC input, a DC output of 20 volts at a maximum power of 5 amps, so it's a 100 watt converter. We'll switch at 150 kilohertz. We'll design the current ripple in our magnetizing inductor to be 20% of the DC component. Design this for duty cycle of 0.4 which means the turns ratio is 0.15. We'll allow a copper loss of 1.5 watts. Typically in an application such as this, we need insulation between the primary and secondary, so we'll choose a fill factor smaller than 0.5, and I've taken it here to be 0.3. And we'll design for a maximum flux density of 0.25 Tesla so that we don't saturate our transformer at maximum temperature. On the left-hand side of this slide are the basic calculations for design of the flyback converter. This is from an earlier course. So the DC component of magnetizing current is the load current divided by D prime and then reflected through the turns ratio to get to the primary. It turns out to be 1.25 amps. 20% of that is 0.25 amps, which will be our ripple delta I. So our peak current is the sum of those, 1.5 amps. We'll choose the magnetizing inductance then to get this ripple, and that turns out to be 1.07 millihenries, referred to the high voltage or primary side of the transformer. We'll need to calculate the RMS values of these waveforms. So the winding currents have waveforms that look like this with I1 and I2. They're pulsating and they have ripple. Appendix A has a list of equations for the RMS values of waveforms such as this. And in fact, equation A6 is the equation for the RMS value of this kind of waveform as a function of its duty cycle and its ripple. We get this expression where capital I is the DC component while the current conducts. D is the duty cycle, and we have a factor that depends on the ripple magnitude. So if we use that formula, we get that the RMS primary winding current is just under 0.8 amps, and the RMS secondary winding current is 6.5 amps. This quantity we call I tot is the sum of the RMS winding currents, all referred to the primary winding. That turns out to be 1.77 amps. Now we have what we need to calculate the core size. When we plug into the kg formula, what we find is we need a core having a K sub g of at least 0.049 centimeters to the 5th power. For this example, I'm going to use an EE core. We can look in Appendix B in the table for EE cores. Here is the EE core table. 0.049. Looks like an EE22 is not large enough. We need an EE30 with 85.7 times 10 to the minus third for K sub g. So this is an E core whose long dimension is 30 millimeters. Given that choice, now we can calculate the air gap and the turns. Plugging into our formula for air gap, we get 0.44 millimeters for total air gap. With that air gap, we can choose the primary turns. That turns out to require 58.7 turns. Scaling the secondary turns by the turns ratio, we find we need 8.81 turns on the secondary. Of course, we have to round this, so we could round to 59 turns on the primary and 9 turns on the secondary. Next, we determine the wire gauges, so we have to calculate the alphas. In a converter such as the flyback converter, the RMS values of the winding currents do not necessarily scale with the turns ratio. And what we find here when we calculate the alphas is that the primary gets 45% of the winding area and the secondary gets 55%. So we don't get 50% to each winding. The reason for this is that this converter is operating with a duty cycle less than a half, so the secondary conducts for more of the switching period than does the primary, and it's worthwhile to allocate more of the window area to the secondary as a result. When we use these alphas to calculate the wire gauges, here are the wire gauges that we need. We can look in our wire table in the Appendix B and find that for the primary we need 28 gauge, for the secondary we need 19 gauge. I would add here that 28 gauge probably is not very many skin depths and will not have too much skin effect or proximity loss. 19 gauge is pretty big wire, and we may want to look at using Litz wire or foil to reduce the proximity loss of the secondary. Having determined the design, besides the AC copper loss, we should also look at the AC core loss and verify whether it can be safely neglected or not. For this application, we have small ripple, 20% current ripple. The H field in the core is proportional to the current, and so is the B field through the permeability of the core. So what we find is that the flux density, B, will ramp up and down in proportion to the current in the magnetizing inductance. So we have a small minor loop for our BH loop corresponding to this variation in B. In fact, from Faraday's law, we know that the derivative of B is equal to 1 over NAC times the voltage, and we can integrate both sides of this to calculate B, and it's very similar to integrating V as L di dt to find the current ripple. During the first interval, we have a constant applied voltage. If you put a constant here, Vg, in for the voltage, then that says that B increases with a constant slope given by the applied voltage over N1AC. So we have a slope here that is the applied voltage Vg over N1AC, and 2 delta B then is this change. That's equal to the slope Vg over N1AC times the time, which is dTs. So then we can solve for delta B. Delta B would be Vg dTs over 2 N1AC. We can plug these numbers in now for our design, calculate delta B, and then estimate the core loss. Here is that formula I just wrote. We plug in numbers and we find that delta B is 0.041 Tesla. To find the core loss that results from this, we need to look at the manufacturer's data sheet. Here's a typical plot, and let's suppose that this is the plot from the manufacturer's data sheet for this core loss. On the horizontal axis, we have delta B, which is the peak AC flux density in Tesla. And on the vertical axis, we have the power loss density, which is the watts per cubic centimeter of core material. If they give us a 150 kilohertz plot at 0.41 Tesla, then we can read off the power loss density. It looks like it's about 0.04 watts per cubic centimeter. So we can plug that in. We need to multiply that by the volume of the core. If we look on our core data table, we find that the cross-sectional area is 1.09 centimeters, and the magnetic path length is 5.77 centimeters. Multiplying those two together gives us the volume. When we multiply that by the power loss density, we get a 1/4 watt. Okay, we designed for a copper loss of 1.5 watts. There will of course be proximity loss as well that we should account for. And we're finding now that the core loss is another 1/4 of a watt. The core loss is small because the ripple is small and delta B is small. So it's not a bad approximation to ignore the core loss. Now that we've designed our device, we can calculate the core loss, see what it is, and if we want to, we can further adjust our design. But neglecting the core loss is indeed a reasonable approximation for this particular example. Because the flyback converter for this design operates in the continuous mode with small ripple, then the core loss is small and the design is dominated by the copper loss. We should also go back and check the magnitudes of the skin and proximity losses. In the last chapter, we discussed how to design an inductor given the constraints of allowable DC copper loss, and maximum flux density to avoid saturation. Now I want to extend that discussion to consider optimization of transformers, where the core loss is important as well. In these applications, we need to minimize the sum of the total copper plus core loss. The operating flux density is no longer simply constrained by saturation. Rather, we choose a smaller flux density that manages the core loss to optimize the total loss. So in this chapter now, the flux density is no longer given, but rather is a variable to be found such that the total loss is minimized. We'll consider a multiple winding transformer, and we'll use the results from the last chapter of how to optimize the window area and its allocation among the various windings. We're going to write the constraints for transformer design in this lecture, and then we'll do some examples and look at how increasing the frequency can reduce the core size, so that a 100 kilohertz 100 watt transformer might be only this large, whereas a 60 hertz 100 watt transformer is much larger and requires a large amount of iron. Again, this lecture covers the basic constraints of transformer design. We'll use these constraints to develop a first pass design procedure similar to the KG method from the last chapter. We'll work some examples. We'll also look at AC inductor design, where the ripple is large, and we'll summarize. What are the equations that are the basic constraints of a transformer design? Since we're considering core loss, first we need to write the equation for core loss. We previously talked about this. We will use the empirical Steinmetz type equation, in which the core loss depends on a constant multiplied by delta B, the AC component of flux density, and it's raised to some power beta that is an empirical number, multiplied by the volume of the core, or its cross-sectional area times its path length. Typical values of beta for ferrite might be 2.6 or 2.7. Generally, increasing delta B increases the core loss very quickly, and greater than a square law. We'll use this equation as the first design constraint. Second, we need to work out delta B. Let's assume that for winding 1, we have some arbitrary voltage waveform V1 of t applied, and maybe it looks like this. Since this is the winding of a magnetic element, the volt-seconds have to balance. And we're going to define lambda 1 as the volt-seconds applied to the winding during the positive half of the waveform. So this area here are the net volt-seconds, which make the flux and magnetizing current increase. Of course, during the second half of the cycle, we have equal and opposite or negative volt-seconds that bring the flux and the magnetizing current back down to where they started. We can then define lambda 1 as this area, so it's the integral of the voltage between the zero crossings. We know from Faraday's law, V1 is equal to N1 AC times dB dt. Therefore, the change in B over this half cycle is 1 over N1 AC times the integral of the voltage. And this is from one zero crossing to the next, so from T1 to T2. It's traditional to call delta B the peak rather than the peak to peak, so we need to divide by 2. This here is our lambda 1, and so we get that delta B is lambda 1 over 2 N1 AC. This is our second constraint, and you can see that the volt-seconds applied to the primary winding control the flux in the core, and in particular they control delta B. To obtain a given delta B, then, this tells us how to choose N1. We can solve for N1 and get this, so that if we want to reduce delta B, we can increase N1, and therefore we can control the delta B at which we design our transformer to run. The third constraint is the copper loss. In the previous chapter, we found how to allocate the window area among the various windings to minimize the total copper loss, and this was the result that we got. Here, this quantity I tote is the sum of the RMS currents of the windings, all reflected through to the primary winding. When we optimally allocated the window areas among the different windings, then we got this total copper loss. And so we'll assume that we do that and that we use the alphas from that previous chapter result. The copper loss depends on N1, actually on N1 squared. We can go back to the previous slide where we solved for N1, and we can plug that into this equation to eliminate N1. When we do that, here's what we get for the total copper loss. So the copper loss varies like 1 over delta B squared. As you increase delta B, the copper loss goes down very quickly, and in fact it goes down like the square. What we want to do is minimize the total power loss. So the sum of the core plus the copper loss. Here is our equation for core loss from Steinmetz equation, which increases as delta B to this beta power, where beta is a number typically greater than 2. And here's the copper loss from the last slide that goes down like 1 over delta B squared. And so the sum is the sum of these two, and it looks like this. There's a minimum. In fact, the total core plus copper loss occurs at some optimum value of delta B, where the sum of these two quantities is minimized. If you look at this plot, P tote has zero slope, where the negative slope of the copper loss cancels the positive slope of the core loss. They have equal and opposite slopes, and there's where the minimum occurs. It's not necessarily where their values are the same here, but it's where their slopes are equal and opposite. We can solve for that optimum B. So again, we take these derivatives, and where the slopes have equal and opposite values, we find the minimum. Here are the equations to do that. Here's our core loss equation. Here's our copper loss equation. Take the derivatives of those to get these equations. We can equate them or plug them into the previous formula. When we solve them, delta B turns out to be this expression. Given that solution for the optimum delta B, now we can find the total loss. If we plug this delta B into our PFE and PCU equations and add them together to get the total loss, this is the result. The equations are getting a little bit big, but we can still manage this equation. We can rearrange this in a way similar to the KG design method, where we put all the quantities that depend on the core geometry on the left-hand side. We put all the specifications on the right-hand side. And then we can derive a first-pass design procedure for selecting the core that's similar to the KG design method. I'm going to call the left-hand side of that equation KGFE. So it's a function of the core geometry, which is the window area, the cross-sectional area, the mean length per turn, and now the magnetic path length also. And it also depends on beta, which is a function of the core material properties. So all of these things we can put on the left-hand side of the equation. The right-hand side are the quantities that are specifications and that we take as given. The core tables in Appendix D also list KGFE as well. They list it for a given value of beta, I believe 2.7. Thus we find the optimum delta B that minimizes the total core plus copper loss, and delta B now is a variable in our design rather than a given specification. We can calculate the KGFE required for a given application using the formulas on this slide. to select a core that is large enough to do the job. Once we've found that core, then we can go back from the earlier equations and compute the turns and wire gauge and so on. This lecture summarizes a first-pass design procedure for a transformer based on the design equations of the previous lecture. Here are the quantities that we must specify at the outset. I tot, as usual, is the sum of the RMS winding currents, all referred through the turns ratio to the primary. We have our desired turns ratios. As we discussed in the last lecture, we have the applied primary volt seconds, lambda 1. We have P tot, the total copper plus core loss that we will allow. As usual, there's the fill factor. And then we need to have an idea of what core material we're going to use and know its Steinmetz equation parameters, the exponent beta and the coefficient KFE. The equations include these other quantities, which we will find, and here are the units that the equations of the following slides express those quantities in. In the last lecture, we derived a process that was similar to the KG design method for inductors, but that incorporated both core and copper loss. The result was this figure of merit of a magnetic core, as how big it is magnetically for a transformer design where core loss is important. The right-hand side is a collection of the specifications. From this equation, we can plug in the specifications and evaluate how large a core we need in terms of its KGFE. The ferrite core tables of Appendix B include values of KGFE. It's the third column in the tables. The value of KGFE depends not only on the core shape but also on the material parameter beta, and these numbers here are given for beta equals 2.7. Having selected a core, now we can evaluate delta B, the peak AC flux density. Here was the equation from the last lecture for that. The core dimensions are expressed in centimeters, and there's a factor of 10 to the 8th to account for that. This delta B then is in Tesla, and it is the peak AC flux density. At this point, we should check to make sure the core won't saturate. If delta B is too large, then it's possible that the maximum flux density will saturate the core. In that case, we should go back to the KG method from the last chapter to specify a B max that does not saturate. But assuming the core doesn't saturate, then this is the optimum delta B that minimizes the total loss. Next, we evaluate the number of turns. Here was the expression for the primary turns as a function of the delta B from the last slide. Knowing the primary turns, we can choose the turns of the other windings according to the desired turns ratios. Knowing the turns of all the windings, now we can choose the wire sizes. We calculate the alphas, or the fraction of the window area allocated to each winding, as usual, according to the amp turns of each winding. And then, knowing the alphas, we can find the wire gauges and look up the wire sizes from the wire table in Appendix B. So then we have a first pass transformer design. Now we should check that design. Here's an equivalent circuit for the transformer. The magnetizing inductance then is given by this expression, where we know the number of turns now in the core, so we can calculate L sub m. This peak magnetizing current is really the AC current ripple in Lm. So really this is delta IM, is what we'd normally call it. We can calculate the winding resistances as usual, or the DC resistances of the windings using rho times the length over the area of the wire. And finally, we should also calculate the proximity loss. So if we know the wire sizes, then we can figure out how many layers are in each winding and do the proximity loss calculations as in Chapter 10. If any of these quantities are unacceptable, then we may want to iterate our design further. So we have the tools to do a first pass design of the transformer, and this is really what you need to be able to go into the lab now and actually wind a transformer for your switching converter. Let's do a transformer design example. Here is an isolated Chook converter, and we're going to design the transformer of this converter. In this particular example, we're converting 25 volts input to a 5 volt output. The Chook converter is an inverting buck boost type converter. To get a positive output, we'll reverse the dots and reverse the direction of the output rectifier diode. And so in this case, the output voltage V is the input voltage, Vg, divided by this turns ratio N, times the Chook conversion ratio d over d prime. We're going to design this converter for 100 watts and a switching frequency of 200 kilohertz. With a turns ratio N of 5, this converter will work at d of a half to get an output voltage of 5 volts. We'll take a fill factor of a half, and we're going to allow a quarter watt of total loss, which is a pretty low number in a 100 watt converter. Let's also suppose that we've chosen to use magnetic zinc P material. Nothing special about that, it's simply a ferrite core material that works well at 200 kilohertz. For this material, the Steinmetz parameters we can find from the data sheet for this material are KFE of 24.7 and beta is 2.6. With these numbers, here are the waveforms of the transformer. The applied primary voltage is a pulsating waveform whose volt-seconds balance. We're operating at d of a half. Vc1, the primary side capacitor voltage in the Chook converter, is the same as the input voltage Vg, or 25 volts. Lambda 1, the area in the positive part of the applied voltage waveform, then is this 25 volts multiplied by the duty cycle of a half times the switching period of 5 microseconds. So what we get works out to be 62.5 volt microseconds for lambda 1. We also need to calculate the RMS winding currents and this quantity I tote. From solution of the Chook converter, we find that the transformer winding currents have waveforms that are pulsating and look like this. They have the same waveform and simply are scaled by the turns ratio. The RMS value of this pulsating waveform is the square root of d times the current during the first interval squared plus d prime times the current during the second interval squared. That works out to be 4 amps for the primary. The secondary is similar. It's just scaled by the turns ratio, so it's 5 times bigger, and we get an RMS secondary current of 20 amps. The I tote quantity then is the 4 amps for I1, plus the 20 amps scaled through the turns ratio. 20 amps divided by the turns ratio of 5 gives us another 4, and I tote turns out to be 8 amps. Given that, now we can evaluate KGFE and choose the core size. We plug into our KGFE formula. This is the resistivity of copper. Here's the lambda 1 volts seconds. This is I tote, 8 amps. 24.7 is the KFE of the core material, and so on. When we evaluate, we find that we need a KGFE of at least 0.00295. We go to Appendix B and look in the core tables. For no particular reason, I'm going to choose to use a pot core type geometry. Here's the column of the KGFEs of these. and it looks like the 2213, the 1811, the next smaller core size is too small. Therefore, we'll choose a 2213 pot core. For reference, this core has a diameter here of 22 millimeters, and it has a height from the side view of 13 millimeters. The table also lists the thermal resistance. This is the temperature rise of the center post of the core under normal conditions, in other words in the air but without any extra fans, and it's an approximate number. We have a 1/4 watt of loss, so if we multiply that by 38 degrees C per watt, we would get, what, a 9.5 degrees C temperature rise in this device. A 10 degrees C temperature rise is a very conservative number. We could easily push this to 20 or 30 degrees C in a typical design. Indeed, if we were able to use the next smaller core, the 1811, with its thermal resistance of 60 degrees C per watt, our 1/4 watt would still give only a 15 degrees C rise. It certainly looks like this core will work. So we select the 2213 pot core. Next, we can evaluate delta B for this core. We plug in the core dimensions and our specifications into the delta B formula from the last lecture. And what we find when we evaluate that is that our delta B is 0.0858 Tesla. These ferrite core materials saturate at about 0.35 or 0.45 Tesla. So this is well below the saturation flux density, and so this core should have no problem. And indeed, the optimum flux densities of transformers that operate in around the 100 or so kilohertz are on the order of 0.1 Tesla. So this is certainly in that range, and for modern ferrite core materials is a typical value. Next, we evaluate the number of turns. We find that N1 needs to be 5.74 turns. If we divide by the turns ratio, then we get that N2 should be 1.15 turns. Of course, you can't have fractional turns. The turns have to be an integer, so we have to round this off. To get the turns ratio of 5 to 1, we'll need to choose N1 then to be 5 and N2 to be 1. So we're going to run with a little lower number of turns, which means we'll have a little bit higher delta B and a little higher core loss than expected. Next, we allocate the window area among the windings. To calculate the alphas, we allocate the window area according to the amp turns of the windings. When we plug in, we find that both alpha 1 and alpha 2 are 0.5, so we give half of the window area to the primary and half to the secondary. Given that, now we can evaluate the wire areas and find the wire gauges. We get these values for the wire cross-sectional area, the bare area. We can look in the wire table at the end of Appendix B and find that the primary should be 16 gauge and the secondary should be 9 gauge. So we'll have 5 turns of 16 gauge for the primary, 1 turn of 9 gauge for the secondary. Now, these are very big conductors, especially the 1 turn of number 9 gauge. 9 gauge wire is very large. In fact, it's really not a practical solution for a pot core having these dimensions. So in practice, what we would do is look for alternatives to 9 gauge wire. We could use several smaller gauge wires in parallel and wind them, and perhaps they would fit and be easier to wind. Sometimes in an application like this we use foil windings, where we use copper foil instead of round wire, or maybe Litz wire, or again some parallel strands of wire. Having designed the transformer, now we should go back and evaluate the losses to check how the design came out, given the various things we had to round off. I would especially in this case want to go back and check the proximity loss and perhaps rearrange the conductors in some way to minimize proximity loss with these very large conductors. It's interesting to look at how the core size varies with switching frequency. We can take our KGFE formula and evaluate it for different switching frequencies to see how switching frequency affects the core size. Here's the result for this application. The bar charts are actually just the core dimensions. So at 25 kilohertz, the KGFE formula requires the largest pot core on the list, the 4226. So this is 42 millimeters in diameter and 26 millimeters tall, and it's a large core. As we turn up the switching frequency, the core size goes down. And here's our 200 kilohertz design we just did with a 2213. Also plotted here are these data points, which are the delta B in Tesla. The delta B is kind of wiggling up and down. Really, that's just because of quantization of the core sizes. If we could have smoothly varying core sizes, this would be a smooth function. The minimum seems to happen at about 250 kilohertz. So if we turned up our frequency a little more, we could make this transformer work with the 1811 pot core. If you keep turning up the frequency, what happens is the core size goes back up. And in fact, you can see why this is because at these higher frequencies, the core loss is starting to go up very quickly, and we're having to turn down delta B in order to limit the core loss. This always happens, and there is an optimum frequency for a given application and a given core material that minimizes the core size. Of course, we haven't included everything in this formula, and in particular, we haven't included the proximity loss. There are papers in the literature where people have written big computer programs to do detailed optimizations, including all the losses. They may be able to up the frequency a little bit and get a little bit lower optimum core size, but generally what they find is that qualitatively this is correct. The core size goes down and then comes back up, and there's an optimum switching frequency. We see designs in the literature with the latest core materials that may be optimized at a megahertz, but it depends on the application. And in some applications, the optimum is, say, 250 kilohertz or even lower. Now let's do a second example in the design of a transformer of a 2-output full bridge buck-based converter. Here's the schematic. We have a 160 volt DC input, which is what we might get from rectifying the 120 volt AC power line. We have two isolated outputs. We have a 5 volt 500 watt output, so 100 amps of DC load there. And we have a 15 volt 15 amp output. That's 225 watts, so this is a 725 watt converter at full power. We're going to design the transformer of this converter. We have a single primary winding that handles all of the AC input power. The secondary windings are center tapped, and we have full wave rectifiers on the secondary sides. In this converter, there's usually a little confusion about how the switching frequency is defined. 150 kilohertz for this example is the frequency of the switching ripple in the output inductors. Our transistors will switch on and off at 150 kilohertz, except they alternate. In succeeding switching periods, we use the opposite devices. This applies a 75 kilohertz waveform to the transformer. So really we're designing a 75 kilohertz transformer and then 150 kilohertz output filter inductors. In design of the converter, we've decided to choose a turns ratio of 110 on the primary to 5 for the main output and to 15 for the second output. We're going to optimize the transformer to operate at duty cycle of 3/4. For this example, we're going to design using magnetic zinc ferrite P material. From the data sheet of that material, at the transformer frequency of 75 kilohertz, the Steinmetz parameters are the KFE is 7.6 and beta is 2.6. We'll also use an EE core for this design. There are nice large EE cores that are appropriate for the 725 watt power level. We'll take the fill factor to be 0.25. The fill factor will be lower in this example than in some previous ones because we have multiple windings and we have isolation for safety reasons between the primary and secondary. We're going to allow a total transformer power loss of 4 watts, which is just over 0.5% of the output power, and we'll use copper wire. Here are the waveforms for the transformer and the full bridge converter. The primary has a rectangular waveform like this, and here I'm defining T sub S is this time. And so this would be 2T sub S right here. So half of the primary side transistors conduct for time DTS, where the input voltage VG, that is the 160 volts, is applied to the transformer primary. Then for the D prime interval we apply 0. During the next switching period we alternate the primary transistors to apply negative VG during the second switching period. The applied volt seconds, lambda 1, then would be this area, which is the VG input 160 volts multiplied by DTS. The primary current follows the primary voltage. During the D interval, the transformer primary current is the sum of the reflected load currents from the 5 and 15 volt outputs. The secondary side winding currents look like this. We've discussed this in the past, where in 1/2 of the center tapped output we may have a current waveform that looks like this, where the load current conducts for the DTS interval. Then during the D prime interval we get the load current splitting between the two output windings, half going in each. And then during the next switching period we have 0 during the next DTS interval. Then here is lambda 1, the applied primary volt seconds. For this nominal design point we have 160 volts as VG. This duty cycle is 3/4. So we'll have duty cycle of 3/4 multiplied by TS, 1 over 150 kilohertz, which is 6.67 microseconds, and we get a lambda 1 then of 800 volt microseconds. The primary current waveform, which looked like this, has an RMS value that is the square root of the duty cycle multiplied by the on-state current. When we reflect the two load currents through their respective turns ratios and multiply by the square root of the duty cycle, we get an RMS primary winding current of 5.7 amps. The secondary winding currents for each half of the center tapped secondaries have waveforms like this. We can look in Appendix A to find an expression for the RMS value of this waveform. What we get is 66 amps in the main output, the 5 volt output windings, and 9.9 amps in the 15 volt output windings. So then this quantity I tot is the sum of the RMS currents of the windings referred to the primary side. So it's the primary current I1, 5.7 amps, plus this secondary RMS current, 66 amps, pushed through its turns ratio of 5 over 110. There are 2 of those, since we have 2 secondary outputs. And we have the 9.9 amps for the 15 volt output RMS currents multiplied by that turns ratio, and there are 2 of those. We get 14.4 amps. Now we're ready to select a core. We plug these values into our KGFE formula, and what we find is we need a core with a KGFE of at least 0.00937. We can look in Appendix B, or magnetic core tables, for EE cores, and what we find is the smallest EE core that satisfies this inequality is the EE40, whose KGFE is 0.0118, so a little slightly larger. There's a little bit of margin. Incidentally, an EE40 core has a height, or this distance from here to here, of 40 millimeters. Knowing the core, now we can evaluate the other equations using the core dimensions for the EE40. Our expression for B max was this. When we plug in the values, we find that our delta B, or the B max, will be 0.23 Tesla. This sounds good. This is certainly less than the saturation flux density. It's a little higher than in the last example because we're operating at a lower frequency. Now we can evaluate the number of turns. When we plug in for the primary turns, we find that N1 needs to be 13.7 turns. We then choose the secondary turns according to the turns ratios that we desire, and we calculate 0.62 turns for the 5-volt output and 1.87 turns for the 15-volt output. Now, we can't have fractional turns, so we have to round these off, and really the dominant constraint here is going to be that we need at least one turn for the 5-volt output. So if that output is one turn, then our 15-volt output will have to be 3 times as many, so that'll go to 3 turns. And then to get the turns ratio of 110 to 5 to 15, it means N1 needs to go to 22 turns. So we're pretty far off from the optimum choice. This is going to change the effective delta B, and it's going to change the loss. Well, okay, let's use those numbers and see what happens. With this choice of delta B, we end up running at 0.143 Tesla, so significantly lower delta B. That'll make the core loss much lower. It'll go down, and turns out, to 0.47 watts, about a half a watt, and it makes the copper loss a lot larger. The copper loss works out to be 5.4 watts, so the total loss is then a half plus 5.4 is 5.9 watts, which is more than our design goal of 4 watts. The fact that we have to round off turns makes our design significantly less than optimum. If we want to meet our goal of 4 watts, we need to use a larger core. So let's use the next larger core on the list from Appendix B. It's the EE50, which is 50 millimeters in length rather than 40. If we repeat the calculations for the EE50, our delta B comes out to be 0.14 Tesla. The optimum N1 is 12, and the total power loss according to the optimum formula would be 2.3 watts. But when we round N1 from 12 to 22, we'll get delta B is all the way down to 0.08 watts. Our copper loss 3.89, iron loss of 0.23, and it works out to be 4.12 watts. That's still more than 4 watts, but let's go with that one. That's close to 4. The alternative is to go to an even larger core, such as an EE60. With the EE50 design, we work out the window area allocations. The primary gets an alpha of I1 over I tot, which turns out to be about 40% of the window area. Each half of the 5-volt output gets about 21% of the window area, and each half of the 15-volt output gets 9.4%, about 10% of the window area. Our wire gauges, then, we need 19 gauge for the primary. We'll need 8 gauge for the 5-volt outputs, which is giant, and we'll need 16 gauge for the 15-volt outputs. For this 5-volt output especially, that's one turn of massive wire, we would probably use a foil winding. This is a 100 amp output after all. So a foil or maybe lits for the 5-volt outputs. 16 gauge is getting on the large side, and we probably use lits and maybe foil for that also. So what we see in this example is that we get an iterative process, even without considering other losses such as the proximity effect, which would give additional iterations to optimize the winding geometry. But rounding off the number of turns led to a significantly non-optimum design, and this is a practical issue. For the EE50 design, the next step would be to work out the number of layers in each of the windings, choose a winding geometry, and work out the proximity loss. To the extent that the proximity loss significantly increases the total loss, we may need to iterate again and go to perhaps the EE60 core. Incidentally, once you know what the impact of the proximity effect will be, it's possible to use that fact to go back and re-optimize the design. What we can do is choose an effective copper resistivity equal to the actual copper resistivity multiplied by this proximity factor, in which the copper loss is increased by the proximity effect. Really, this is the effective ratio of RAC over RDC. So we can adjust the effective resistivity of the wire by that factor and then employ it to re-optimize this design. We've spent the last two modules discussing procedures for designing different types of magnetic devices. I chose several basic classes of devices to illustrate their design. Of course, there's quite a few others, and we can approach those designs in a similar way, in which we write the design equations. We then manipulate them in a way to choose a core that is large enough to do the job, and we work out the other parameters of the design. Here is one final example, and I'm going to just briefly outline how it works. Let's consider an AC inductor design. This is an inductor that's a single winding. We want to obtain a given inductance, but we have to include both core and copper loss. And in the most extreme case, there may be no DC component of current or flux, but there may be a large AC component which causes large core loss and large copper loss. So we might assume that we have a voltage waveform, that is some arbitrary waveform, but we can identify its volt seconds, or this area lambda. There's some inductor current, which obeys the law V is L d I dt for the inductor. And we'll assume that we have a geometry that's topologically equivalent to this, where there's a core, an air gap, and a winding. I'll just outline the equations. We want to obtain a specified inductance. We have the usual equation for inductance, and that's the first constraint. To find the core loss, we need to know delta B, the peak AC component of flux density, and it has the usual relationship that comes from Faraday's law, that B is related to the volt seconds lambda. We need to calculate both the core loss and the copper loss. The copper loss is given by this expression that really just comes from the equation for the resistance of the wire, and this is ignoring proximity effect. And we have our usual equation for core loss that comes from Steinmetz's equation. As usual, we can combine these, but now subject to these constraints, to find the value of delta B that minimizes the total loss. When we take the derivative of the total loss, set it equal to 0, and solve for delta B, then we find that this is the optimum flux density. And with that delta B, then we can find the core KGFE that is required to satisfy the requirements. Here is the result in this case. And so as usual, then we will define a procedure where we evaluate KGFE, pick a core that's large enough, evaluate delta B, and then go back and find the turns and the wire size. So in your travels, when you encounter different types of magnetic devices to design, you can follow this basic approach of writing the equations of the constraints, of the total losses, finding the delta B that minimizes the total losses, and use that to select a large enough core and solve for the other design parameters.